This is a comprehension based question. We have been given a passage and we need to determine which of these conclusions can be inferred from that. So it is saying that listening to music during exercise improves performance and reduces discomfort. Scientists research whether listening to music while studying can help students learn better, and the results were inconclusive. So they're trying to say that in case of exercise, the music has been seen to improve the performance and reduce the discomfort. In the same way, when the study was conducted for students, that if they listen to music while studying, then would it benefit them? But the results were inconclusive. Students who needed external stimulation for studying fared worse, while students who did not need any external stimulation benefited from music. So they are talking about two categories of students. There is one class of students who do not need any external motivation for studying. They will do it on their own. So this category of students benefits from listening to music while studying. While there is another category of students who need some external stimulation. They need someone to keep a gun on their head and make them study. So that class of students did not benefit from music. They performed even worse. So now based upon this passage, let us have a look at the options. Listening to music has no effect on learning, positive effect on physical exercise. This part is definitely true, but it is not definitely correct that it has no effect on learning, because it does positively impact some students, one category of students. So because the results were inconclusive, we cannot say this for sure. This answer is incorrect. Listening to music has a clear positive effect on both exercise as well as learning. On exercise, it definitely has, but for learning, we just saw it depends upon students. We cannot generalize. So again, it's incorrect. It has a clear positive effect on physical exercise and positive effect on learning only in some students. Yes, this is correct. For some students, it has a positive effect, while for others, it has a negative effect. So we can go with this option. The last one is saying that it has a clear positive effect on learning in all students. This is incorrect. Only for some students it has a positive effect. So this option is also incorrect. We'll be going with option C. This is a spatial aptitude question. We have been given a sheet of paper on which this figure is initially drawn, and this sheet is folded along the dotted lines. So it is folded something like this. The first flap is lifted and it is placed on the other side. We need to determine what would be the resulting shape after doing this thing. We need to assume that the shape which is currently present on this first side would get reflected upon the other side and both will be combined together. So basically what we need to do is we'll just take the mirror reflection of this first side and draw it on the other side, assuming this dotted line to be the mirror. So for this lower curve, it will be reflected and become something like this. The leaf shape will be formed on the other side, and for these two little lines, they are facing upwards, they are vertical, so their direction will not change, just that they will be lifted from here and transferred to here, so they will stay the same like this. Hence this will be the resulting shape we'll be having after folding the paper, and that has been given in the option B, so that is our correct answer. This is an English aptitude question. A fill in the blank type of question has been given. Gauri said that she can play the keyboard dash her sister. So here we have two entities or two subjects, Gauri and her sister, and the object is keyboard over here. Gauri and her sister both are involved with this keyboard in some sense. So we can have either a comparison over there that Gauri can play better than or not so better than her sister, or we can have something like both Gauri and her sister can play, or we can have Gauri can play but her sister cannot play, something like that. And as we know about the degrees of comparison, they can be positive, comparative, superlative. So let us look at the options that which of them fits well over here. The first one, as worse as. Now this as worse as is a comparative type of thing, but it does not suit very well over here. Gauri can play as worse as her sister. It's not logically very much appreciable, so we won't go with this option. The next one is as well as, means Gauri as well as her sister. Both of them can play the keyboard. So this may be a suitable option. Let's hold on to this and look at the other ones. As better as. This as better as does not make any sense. It should have been Gauri plays better than her sister. As better as, it's like saying Gauri plays better but same as her sister. So again, it's meaningless. And the last one, the same thing is there. As nicest as means Gauri is nicer as well as similar. So usually this as something as comparison is used when both are equal. Now if they are saying she is better or she is nicer, then as cannot be used with that. So again, these two options are rejected. We'll go with option B, as well as. This is a analogy based question. We have been given an association of pen to write, and in the similar fashion we need to determine what would be the corresponding for knife. We should take care that we form a similar logical relation that was used in this first association rule, which was pen and write, in this second one for knife and the corresponding answer. So in this first case, we can see that pen and write, what's the relation between them? Pen is an instrument that is used to write. So pen is used for writing. In the same fashion, here we would be placing a word which would be associated with knife in the same fashion. Knife is an instrument which is used to dash. What do we do with a knife? We cut the things. So here the correct option of fitting would be cut. So we'll be going with option D, which is cut. Aptitude question. We have been given that the number of students in 3 classes is in the ratio 3:13:6. Let us assume there are 3 classes, A, B and C, and keeping the common ratio as x, the number of students in each class will be 3x, 13x and 6x. If 18 students are added to each class, so now this becomes 3x plus 18, 13x plus 18 and 6x plus 18. This ratio changes to 15:35:21. So now let us say this ratio has become 15, the number of students has become 15y, 35y and 21y. The total number of students in all the 3 classes in the beginning was, that is what we need to determine. So we can use the proportion rules over here, taking 2 at a time. We can say 3x plus 18 upon 13x plus 18. And what's the ratio? For A and B, 15 and 35. Y will get cancelled out. So we get 15 on 35. Again, we'll cancel this with 5, 3 times and 7 times. Now let us cross multiply. We'll get 21x plus 18 sevens. How much is it? 8 sevens, 56, and 5 over here is 126, equal to 13 and 3 39x plus 18 thrice 8 thrice 24, 4 and 2 54. So from here we get 39x minus 21x, that would be 18x, equal to 126 minus of 54, so 2 and 7. 18x equal to 72. So from here we get the value of x as 4. Hence the total number of students initially will be 3x plus 13x plus 6x, and that gives us 13 and 6 19 and 3 22x, and the value of x we just now got is 4. So this becomes 22 times of 4, which is 88 students. So initially in the class there were 88 students, and after addition the ratio changed to 15:35:21. We could have also taken another like comparison between B or C, A and C. Anyway, the purpose was to get the value of x, which we got from just using A and B. So the correct option is C, 88. Type of question. We have been given a bar graph which mentions the number of units of a product sold in 3 different years and the respective net profits on profits on this side in rupees, and the years are mentioned in the x-axis. The cost per unit in year 3 was rupee 1. So cost per unit is given to us in year 3, it was 1 rupee, which was half of cost per unit in year 2. So in year 2 it would have been 2 rupees, and it was 1/3 of cost per unit in year 1. So in year 1 it would have been 3. Now they're saying the taxes were paid on the selling price at 10%, 13% and 15% respectively for the 3 years. So here we have 10, 13 and 15 respectively. The net profit is calculated as difference between selling price and sum of cost price and taxes. So they have given the formula for calculating net profit as selling price minus the cost price plus taxes. But this net profit is already given to us in the bar graph. We need to calculate the ratio of selling price in year 2 to year 3. So for calculating the selling price, net profit is already given. Tax is calculated on selling price itself, so that is also unknown. And what about the cost price? It is also given in the bar graph. We can calculate that. The number of units are mentioned by this shaded portion. In year 1 there are 100 units sold and the cost per unit is 3 rupees. So the cost price which the company required for buying these 100 items was, this 3 is the cost price, not the selling price for 1 unit. Hence for the 100 units the cost price would be 100 times 3, so 300. In year 2 it will be 200 times 2, 400. Here it is 300 times 1, so 300. So we have got the cost price as well. Now how do we calculate the selling price? We will put the cost price and net profit in this formula and then get the selling price. So for the year 2, the net profit given to us is 296. So we can write 296 equal to the selling price, call it as, minus cost price. What is the cost price for year 2? 400. Minus plus tax. How much is the tax to be paid in year 2? 13%. So that will be 13 upon 100. And upon what is the tax paid? Upon selling price. So again here it will be S. So we get 296 equal to S minus 400 minus 13 S by 100. So we will need to solve this equation to get the value of S. For year 2 we will get the value of X as S to be 800 rupees. Similarly we'll calculate for the year 3. The profit given to us is 210. So that will be selling price minus cost price. How much is cost price for year 3? 300. 300 plus the taxes, which will be 15%. So 15 by 100 times S. So we get 210 equal to S minus 300 minus 15S by 100. Solving this equation again, we will get the value of S as 600 rupees. So what we get is in year 2 we have the selling price as 800 rupees and year 3 it is 600 rupees. We wanted to find the ratio of the selling prices in year 2 to year 3. So what do we get? For year 2 it is 800, for year 3 it is 600. Hence the ratio is 4:3. So that is our answer, option D. This is a spatial aptitude question. We have been given the broken piece of a puzzle and we need to identify from which of the given options it will properly fit into, forming a rectangle. Now we can flip or rotate this piece to assemble it. So looking at this, we basically need to match these crevices corresponding to the options. We can see very first it has this square thing, empty square. So in the option, correct option, we need to have this thing at the beginning, but in none of them we can see that. So let us try flipping this piece once. If we flip it anti-clockwise this way, 180 degrees, it would become something like this portion would be coming first. So this is how it should become. Then this portion, and then this one, this direction will be changed. After that we have this thing, and finally this over here. After that this portion, for that we'll be having something like this. So this is what we'll be getting after flipping it once, and let us see now if it fits into any of the given options. Now as we can see, the option D will be discarded because it is having a flat structure over here, but we wanted a pointed structure which would fit into this crevice. So this is rejected. Option elimination would be a better method to use in this case. And now looking at other options, even this option B will be discarded because for this crevice we need a figure like this. So a knife-like figure is required, and that is not present at this place in option B, so this will also be discarded. Now from options A and C, both of them look quite similar except for the difference in the height of this structure. Other than this, those are completely similar. So now let us see how deep do we need this particular crevice to be. In option A, it's more deeper as compared to option C. And when we look at the original figure instead of our drawing, we can say that there is a little gap left over here. Same goes for the option A, while it seems to be a little larger in option C. So the proper fit in this case for this, the gap would be occupying this particular shape, and it is long enough. So it would be fitting properly in this A option, and it won't be possible to occupy that in this particular length. So we'll be going with the correct option as A. This is a simple algebraic question. We have been given an expression. We can evaluate that and then find out the value of x which satisfies this equation. So let us start by expanding the left hand side. We have x minus half the whole squared. So we'll be applying a minus b the whole squared on that to get x squared minus 2x 1 by 2 plus of 1 by 4 minus same thing for x minus 3 by 2 the whole square, x squared minus 2x 3 by 2 plus of 9 by 4. Simplifying this, we get x squared minus x plus 1 by 4 minus x squared plus 3x minus 9 by 4. Now x squares get cancelled. We have minus x and plus 3x, that gives us 2x, 1 by 4 and minus 9 by 4, that would be minus 8 by 4, which is minus 2. So we have 2x minus 2 from the left hand side, and right hand side is given to be x plus 2. So now we bring this x over here to get 2x minus x equal to x, 2 plus 2, 4. So the value of x we got is 4. Let us also check if it satisfies the expression. 4 minus half, that would be, we can write 4 to be 8 by 2. So this thing would become 8 by 2 minus 1 by 2, 7 by 2 the whole square, 49 by 4 minus of x minus 3 by 2. So 8 by 2 minus 3 by 2, 5 by 2 squared, so 25 by 4. This will become 49 minus 25, that would be 24 by 4 equal to 6, and 4 plus 2 is also 6. So yes, 4 is satisfying this expression, and hence the correct option would be C. This is a simple geometrical question. We have to consider a cube like this, and now in this cube we'll be drawing the longest diagonal. How will that diagonal be? Let us name the vertices of this cube as A, B, C, D, E, F, G and H. Now the longest diagonal for this particular cube will be from, it can either be from C to E, or it can be from B to H, and likewise the one from the farthest point of this particular surface to the farthest point on this particular surface, that would be a longest diagonal. So let us consider this CE to be our longest diagonal. And now in this they are saying that theta is the angle in degrees that the longest diagonal makes with any one of the edges of this cube. So let us say this angle is theta, or we can also consider point E. So in that case, this can be considered theta, or this angle can be considered theta. So it depends upon which side we are considering. We basically have to find the value of cos theta. So for this, let us assume that the side of this cube is A. All the edges will have the same length A. And in this case, if we also connect the edges E and G, then we'll see that this triangle CEG, this will also be a right angle triangle at G. And for this triangle, we also have in the base surface the triangle EF and G. It will also have both of its sides as A, and applying the Pythagoras theorem in this lower triangle, we'll see that the length of side EG, or we can say using Pythagoras, this will become 2 times of A squared, because it will be EF squared plus FG squared. So EG would be A root 2. And now in our triangle CEG, we'll again apply the Pythagoras theorem. With that, the length of the longest diagonal CE squared would be CG squared plus EG squared. CG is already known to us as A, and EG we just found out to be A root 2, so its squared would be 2A squared. So from this we get the length of CE, or our longest diagonal, to be A root 3. Now let us apply the cos theta property in this triangle CEG. We know that the value of cos theta is adjacent side upon hypotenuse. So considering this angle C to be the theta, what would be the adjacent side? This edge CG. So value of cos theta would be CG upon the hypotenuse, which is CE. And we know the length of CG to be A because it is an edge, and CE we just found out to be A root 3. Hence, cancelling out A, we get 1 by root 3, and that would be the value of our cos theta. So the correct option is C. This is a logical reasoning based question. We have been given 6 students, P, Q, R, S, T and U. All are having distinct heights, and they're comparing their heights, and they make the following observations. First one is saying that S is taller than R. So let us arrange them height wise. S is taller than R. We have the increasing height on this side. So S is taller than R will be represented this way. Now Q is the tallest of all, so it will come over here. U is taller than only one student. So now U can be placed over here if R is the shortest, or U can be placed over here if we have one more student coming over here. In total we have 6 students. So 1, 2, 3, 4, 5, 6, this is a possibility. So for now, let us assume that one student will come over here and U is coming over here. Next, observation 4, T is taller than S but not the tallest. Now T has come over here. So now the only one left is P. So P can come either over here, and then this place will be left blank, not required. All the 4 observations are already satisfied. S is taller than R. Yes, it is holding true. Q is the tallest. It's holding true. U is taller than only one student. We place P over here. So again, this is satisfied. T is taller than S. That is satisfied, but it is not the tallest. So true. This is the possible arrangement that we got. P, U, R, S, T and Q. So now the question is, the number of students that are taller than R is same as the number of students shorter than dash. How many students are taller than R? 3, S, T and Q. So is same as the number of students shorter than dash. For which of these are 3 students shorter than itself? For S, how many students are shortest? 3. For P, 0. For T, 4 are shorter. And for R, it is 2. What did we wanted? 3. 3 students are taller than R and 3 students are shorter than S. So S will be our answer. because it is having the same number of students shorter than itself as is the number of students taller than R. So the correct option is A, which is S. This is a computer networks question based upon TCP connection establishment using the three-way handshake mechanism. Now, what do we know by this mechanism? It is something that is used when two hosts, we can say one is acting as a client and another one is the server, they are trying to establish a connection between them. How does it take place? First of all, client will send a SYN packet to the server saying that I want to initialize the connection. SYN means synchronize, in order to initialize the connection. Now to this request, the server will acknowledge, and server will also send its own SYN package because the connection has to be established from both the sides. So along with acknowledgement, it will also send SYN package to which this client will acknowledge, and that's how the connection would be established between them. So this is something we call to as the three-way handshake mechanism. So now using this mechanism, we are having two hosts in this question, which are P and Q, and they are randomly selecting a 32-bit sequence number, which is X and Y respectively. Now, what is the role of these sequence numbers? We know that TCP is a byte stream protocol, so every byte is numbered. If my sequence number initially is X and I am sending 100 bytes in a segment, let us say, starting from 1 up to 100, this way. 100 bytes are being sent in this segment, so my sequence number would be updated to X plus 100, suggesting that how many bytes have been sent. That is the role of sequence numbers. So now they are saying that suppose P is sending a TCP connection request message to Q. So connection is being initialized from P side towards Q. What is it sending exactly? The SYN bit equal to 1. In this particular packet, the host P would be making the SYN bit as 1. In order to establish the connection, it is initializing it. This is called as active. On P side it would be active connection establishment, or on Q side it will be passive. In the same way, we also have the connection closing mechanism, in which we have active close on this side and passive close on the other side. Along with the SYN bit equal to 1, its sequence number is X, that's already given. Then acknowledge bit equal to 0 because it has nothing to acknowledge till now. So the acknowledge bit it is sending as 0. And this packet has been sent to Q over here. Now to that, Q has to respond. Suppose Q accepts the connection request. Which of the following choices represents the information present in the TCP segment header that is sent by Q to P? So now Q has to accept this connection and send back some response to it. Now what will it respond? P had sent a connection request to it, so it has to acknowledge that. So acknowledgement bit has to be 1. It will also need to establish the connection from its own side. So it will also have to send the SYN bit equal to 1 because connection has to be established on both the sides. Now what about the sequence number? It has initially chosen its sequence number as Y. So it will be sending Y itself because till now there has been no exchange of data on either sides. So the sequence number would be X and Y itself. Now we know that there are two different fields in the TCP header. One is acknowledgement bit and another is the acknowledgement number. What is the difference between them? Let us have a look at these options. We are having SYN bit, sequence number, acknowledgement bit. This is just like a flag. Then acknowledgement number. This acknowledgement number states that what is the next expected byte from the other side. Now from P side, it has received a SYN packet, and that SYN packet consumes one sequence number. Hence the sequence number X has been consumed, and the next byte which will be coming from P would have a sequence number X plus 1. So this is the next expected byte from the P side. Hence Q will set its acknowledgement number as X plus 1 because that is what it is expecting next from P. Then lastly we have FIN bit. The connection is being established and not being terminated, so the FIN bit will be 0. So this is what we have got. Acknowledgement bit 1, syn bit 1, sequence number y. We can check out the options. B is incorrect because syn bit is 0. Then A is also incorrect because the acknowledgement bit is 0. It has to acknowledge the packet sent by P. Then option D is also incorrect because the acknowledgement number given is X, but it has to be X plus 1 because the SYN packet consumes one sequence number. If it were a pure acknowledgement, then it does not consume any sequence number. So here we are left with option C, which is the correct answer. SYN bit 1, sequence number Y, acknowledgement bit or the flag as 1, acknowledgement number, which means the next expected byte X plus 1, and the fin bit 0. So this is the correct answer, option C. A TOC question based upon finite automata. We have been given these 4 regular expressions, and from them we need to identify which of them represents the set of all binary numbers that are divisible by 3. This is an MSQ type question, so multiple answers can be correct. So now it would be easier if we first come up with a DFA representing the set of binary numbers that are actually divisible by 3. And then we can convert that DFA into the regular expressions and check out which of these 4 match with it. So how do we draw DFA for such a language? Let us try with taking some examples and let us see what is the pattern existing between them. Let us take these numbers 3, 6, 9, 12, 15, 18, 21, 24. Yeah, that should be enough. Now for 3 we have 1, 1, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, all ones. Then for 18 it will be 16 plus 2, 18. Then for 21 it would be 16, 20, 21. Then for 24 it will be 16 plus 8, 1, 1, 0, 0. So like that. Now let us try to identify the patterns between them. As we can see in these 2 examples, 3 and 15, we are having even number of ones. Means that is allowed in our language. So DFA for that, let us take it this way, Q1, Q2. Any number of zeros will definitely be allowed. So this is one state. And then even number of ones is allowed. So on 1 we can make these 2 transitions like this. Now these 2 are done. Then we can see 1, 1, 0. That is also covered because 1, 1 then followed by any number of zeros will result into our final state. Q1 itself is our start state as well as final state. So this is also covered. In the same way 24 is covered. Now let us check out for this 21. It is saying 1, 0, 1, 0, 1. So 1 and then we don't have a transition for 0. So let us add another state Q3 for 0. This will be the transition. Then 1, 0, 1, 0, 1. So now if we make a transition for 1 here like this, then 1, 0, 1, and then for 0 will again result into state Q3. It will not take us to the final state. So what we can do is we will loop for 1 in this particular state, and then for 0 we will go back into Q2. So now we get the result as 1, 0, 1, 0, 1. So this 21 is covered. Let us also check out the remaining ones. For 9 it is 1, 0, 0, 1. So the transition would be like this: 1, 0, 0, and then for 1 we are reaching to the final state. So again that is accepted. In the same way we can verify for all the other as well. This is the DFA we'll be coming up with. Now let us look at the options and see which of them actually satisfy this DFA. Now the first one is saying it is a closure this way: 0 plus 1 and then 0 plus 1 followed by 0, 1 star 0, closure followed by 1, and then the closure of this entire thing. So let us try to break it down into different parts. This 0 and closure. So 0 closure, that is accepted in our state Q1. So it is done. Then OR of this particular thing, it is If we consider this closure to be null, then we will be getting simply 1 1 star, which means the even number of ones that we have already covered. Now when we take this value as 1, then that would result into 1 0 1 star 0 followed by a 1. So for 1 we reach into state Q2. After that we are looping into 0 1 star 0, that is over here 0, then this is our 1 star followed by 0. So basically they are removing this state Q3 and bringing it all upon the state Q2. So that will look something like this: 0 1 star 0. This loop has been broken and it has brought down on Q2. So that gives us the option A, which is the correct one. Now let us have a look at the second one. What is it saying? We can do another thing, that we can come up with a minimal regular expression and then check out which of them correspond in the same way to that expression. But we can go directly this way: 0 plus 1 1 plus 1 0 followed by 1 plus 0 0 closure 0 1 and then the closure of entire thing. So now looking at this one, 0 star, that is accepted. 1 1 star, even number of ones, is also accepted. Now coming to this loop, it is 1 0 followed by something and then once again 0 1. So now from this, what are the possible states do we get? This closure, it can take any values from 0 and onwards. So that would give 1 0 0 1 1 0 followed by, now in this particular closure we are having 1 or 0 0. So we can take 1 and we can take 0 0, then follow it up with 0 1. And as we can see, all of these will be accepted by our DFA. This is the trail we can trace out from this DFA as 1 0 0 and 1. We are reaching to the final state that is accepted. And then this we had already seen: 1 0 0 1, and then we can loop out on any number of ones in the state Q3. So this is also accepted. Then 1 followed by even number of zeros and then again 1. So this is our 1. Then this particular loop from Q2 to Q3 will give us even number of zeros and then we end it up with a 1. So that is also accepted. Hence our option B is also correct. Now coming to option C, there is a slight difference between option A and C, and let us check out what exactly it is. This one is saying 0 star followed by 1 0 1 star 0 star followed by 1 star and then the entire closure. So now here we can use the property something like, a plus b the whole star, or the entire closure, that is equivalent to a star b star the whole star. So something like that is existing over here. This 0 star simply means any number of zeros, that is already accepted. Now coming to this one, it is 1 followed by something, then 1, then star of that. And we already know if this closure is giving us null, then we get simply 1 1 star, which is already accepted. Now looking at this particular loop inside, it is 0 1 star 0, and that is the same loop which we saw here in the option A, which comes upon state Q2. So these two are actually same, and hence option C would also be true. Now looking at the last one, let us see if all the 4 options are true for this question. It is saying that 0 plus 1 1 plus 1 1 followed by 1 plus 0 0 star followed by 0 0 and then whole star. So we know that 0 star is accepted, even number of ones is accepted. Now let us have a look at this loop. It is 1 1 followed by something, closure of something, and then 0 0. If this is null, then we get 1 1 0 0. So 1 1 and then 0 0. So that is accepted. Now let us try to substitute some values in this. We can have 1 1 0 0 followed in between with a 1, or we can have 1 1 0 0 and 2 zeros in between, and so on. Let us see if these two are accepted. 3 ones followed by 2 zeros. Let us see. 1 1 and then once again 1 followed by 2 zeros. So 0 and 0. We are not reaching the final state. We simply end it up in state Q2. So this particular string is not accepted. And if one string is not accepted, then we will reject that entire language represented with this regular expression, saying that it is not being accepted by this DFA, or it is not representing the set of binary strings which are divisible by 3. Hence option D is incorrect, and we simply have our answer as A, B and C. So that is the correct options. See question. We have been given a string W and we define WR to be the reverse of W. For example, if W is this string, then its reverse would be given as 10 10 10110, that way. So now from the given options, we need to identify which of the given languages is or are context free. So this is an MSQ type of question. Let's have a look at the first option. It is WX, then reverse of W and reverse of X. And W and X are both given to be lying in 0 and 1's closure. So they can be a null string or any number of zeros or ones combined. So now looking at this string, we are basically having W here and its reverse here, X here and its reverse over here. So if we try to accept this language using a PDA, because we are talking about the context free language, so we'll be using the push down automata. So in that stack, we'll, let us say, push this string W, then we'll be pushing X, but now there is no way to compare this WR against W because X will be on the top of this stack. If we simply ignore this X and we don't push it to the stack, then we can accept W and WR. That is done. But now when this reverse of X will come, by that time the stack would be empty, because we would already have popped this WR against W and we did not push this X at the first place. So when we reach here, the stack would be empty. So now there is no way to compare these X and X bar, or we can say reverse of X. So we can accept either simply W and WR or simply X and X reverse. Both at the same time is not possible using a PDA. So this language will not be context free. So this one is rejected. Now coming to the second one, it is W, then its reverse, X and its reverse. So as we just saw, we can accept this W followed by W reverse. This is actually a palindrome, an even length palindrome basically. So we can accept this W, will be pushing this into the stack, and then when we come to this WR, we will simply pop this W against it. So after accepting this, the stack would be empty. There is X here, and then we'll be doing the same thing for X and X reverse. But now the point is, how do we identify that we have reached to this point and now we need to start popping? For that, we have two different types of context free languages, deterministic and non-deterministic. So non-deterministic would come to our rescue. We can identify the midpoint using that. So it is possible to accept this language, and we can also use another logic, which is W followed by its reverse, it is context free. Similarly, X followed by X reverse is also context free. So if we simply concatenate them, then the resulting language has to be context free, because the CFLs are closed under concatenation. So by that we can say that yes, option B is a context free language. Then in the same way, coming to the third one, it is W, X and WR. So here the restriction is same, both W and X belong to 0 and 1 closure. So here what we can do is, there are two options. Either we can set this X to be a null string, then this will simply be converted into W and W reverse, which will represent an even length palindrome. Or we can set this X to be any string having length 1. In that case, X will represent our midpoint and we will be having an odd length palindrome. and rest of the strings would be covered in W and W reverse. Or we can do another thing, which is we can make W to be a null string. Then this W and W reverse both will be gone, and we'll simply be left with X, and it will accommodate all the strings in 0, 1 closure. So this basically becomes a regular language. And what is that language? 0 plus 1 star. And we know that every regular language is also context free. So this option C is actually representing this language. 0 plus 1, the whole closure, which is regular, and hence it will also be context free. So that also belongs to our answer set. Then coming to the last one, it is W, X, X reverse, and then W reverse. Now for that we can use the same logic, that we can set either X as null or either W as null. Then by doing that, we'll again be able to convert the string into an even length palindrome. Let us say if we just vanish this X out of here, then we'll be left with W and W reverse, which represents even length palindrome. And it is not possible for this particular language to accept odd length palindrome, because we are always having W and its reverse, which will become even length, then X and its reverse, that will also be even length. So even if we just simply remove one of W or X, we'll still be able to accept the same set of strings in this language. Hence even this represents simply W and WR if we set X to be null language. Hence we can say this option D is also a CFL. So B, C and D are all context free languages, A is not. So our answer would be B, C and D. Compiler design question based upon liveness analysis. We have been given a statement S in a program, and for that they have defined these three terminologies. The use of S implies that the set of variables are being used in that S. S is any statement or a line in the program, and use of S simply signifies that there is a set of variables which are being used in that line. For example, if we have a statement like A equal to B plus C, then B and C are the variables which are being used in this particular line. Then we have in of S, which means the set of variables that are live at the entry of S. Now let us say if there is a next statement following it, which is D equal to A minus B. This was the first statement. This is our second statement. So now at the start of this second statement, which variables were live? These two, B and C. So actually the variables which were live at the end of statement 1 will be live at the start of statement 2. That is what it's being implying. Then the third one is out of S, which means the set of variables that are live at the exit of S. So considering this statement 1, which variables were live at its exit? B and C. So now if we are having two basic blocks, basic block is simply a set of statements. This is our block S1, and then this one is S2. These two are the basic blocks, and every basic block has a single entry and a single exit. So if some variables are live at the end of this first basic block S, then they have to be live at the entry of the next basic block S2, because in between there is no way that any variable can be destroyed. So if they are live at the end of first block, then they have to be live at the start of second block. That is what we'll be assuming. So now considering this, which of the following statements is or are correct, that needs to be identified. The first one is saying out of S1 equal to in of S2, which means the variables which were live at the exit of S1 are also live at the entry of S2. That is what we are discussing till now. So the statement has to be correct. If any set of variable is live at this point, then it will also be live in the start of S2. Then next one is saying out of S1 is same as the union of in of S1 and use of S1, which means the variables which are live at the exit of S1 is same as the union of those variables which were live at its beginning and those which were used inside it. Now this is not necessarily true. Let us consider a set of statements like A equal to B plus C, followed by B equal to C plus D, and then we can have something like D equal to A plus B, and finally let's have C equal to B minus A. Now in this we can see that these are the four statements. Now in statement 1, which of the variables are live? B, C and D as well, because D is a variable which is being used in the immediate next line without being defined in between. We not just consider the current statement but also those which are following it. If there is some variable which is not being used in the current statement but it is being used at some later statement without being defined in between, then we consider it to be live at that statement. So at line 1, the variables which are live will be A, not A, B, C and D. A is not live because A is being defined at that particular statement. And then coming to the next one, C and D are being used, so they will be definitely live. B is being defined, so it won't be. Then A is being used in the immediate next line without being defined. So A will also be live at statement 2. Then coming to the third one, A and B are being used, so they are live. D is being defined, so it is not. Then C, it is being defined in the immediate next line, so it will also be not live at this line. So now coming to the last one, A and B are being used, so they are live. C is being defined, so it is not live, and there is no statement ahead of it in which we can check out for a D, so even that will not be considered live. So from these set of statements, we could see that when we say that variable is live at that particular statement, then what does it have to do with those which are before it and those which will be after it? Actually, we can look in between the statements and we can say that all those variables which were live at the end of 2 will be live at the start of 3. And this CDA, this set actually represents the set of variables which were live inside this particular statement 2. So actually when we go to take the union of this in of S1 and use of S1, then that simply means that we are considering, let us call this to be one entire basic block. Then in of S1, which means the set of variables which were live before this block. Let us say A, B, C and D all were live. But then use of S1, which means the variables which were used inside that block. Now in that block we have different statements, and if we consider the entire block as a whole, then we can say there is no single variable which is being used in all of its statements that way. And if we go to take the union, then because this is ABCD, then union would also give us the entire set ABCD. And it's not necessary that it will also be live at the end of block, because inside a block the variables get killed. So it's not necessary that those which were live at its beginning will also be live at its end. Does not matter what happens in between. It's not correct, because in between the variables do get killed. Hence it is incorrect. And coming to the third one, now here they're talking about S1 and on the right side they are talking about S2. Now in of S2 union out of S2, which means those were live at the beginning of S2 and those were live at the end of S2. Again, both need not be same, but one thing is for sure that those were live at the out of S1 will be same as those were live at the beginning of S2. So these two are definitely same, but this is the extra added element, which is the set of variables which was live at the end of block S2. Now it is possible that this is our block S2 and in its beginning only two variables A and B were live, but inside it C and D were also used. So then at the end all A, B, C and D will be live. It is possible that if inside the block, if variables can get killed, then it is also possible that variables can be used again and they are made lively. So it is possible that this out is a superset of in. Hence, the C will also be incorrect because this is the excess that they are adding. Now the last one, out of S1 is use of S1 in union of in of S2. It simply means those were live at end of S1. It will be same as in of S2. But what they are doing, in of S2 then union with use of S1. Now again the same thing. It is possible that at the beginning only two variables were live, but towards the end more variables were found to be live, because inside a block more variables could be made live. So this use of S1 would be adding some more elements, and then we are taking its union with in of S2. So definitely there would be some extra elements added and both the sides will not be the same. So again this is incorrect, and the only one we found to be true is out of S1 same as in of S2, because we can only say for sure that the variables which are live at the end of first block will be also live at the start of the immediately following block, provided that in between there is no leakage, which is generally not the case with basic blocks because they are single entry and single exit. Hence only correct option would be A. This is a DBMS question from indexing. We have a data file which is having 1,50,000 records. It is stored on a hard disk with a block size of 4096 bytes. The block size is 4096 bytes and the number of records is 1,50,000. So now it is said that the file is sorted on the primary key, that is roll number. And the size of a record pointer for this disk is 7 bytes. Let us say record pointer size is 7 bytes, and every student record has a candidate key attribute called enum having a size of 12 bytes. So enum is the candidate key and that's attribute is 12 bytes. Let us say candidate key attribute something, its size is given as 12 bytes. Now suppose an index file with records consisting of two fields, enum value and the record pointer. The corresponding student record is built and it is stored on the same disk. Now one thing to be noted over here is that the primary key is the roll number, and we are not creating the index on the primary key attribute, rather we are creating the index on the candidate key attribute, which is enum. So enum will be unsorted, and when we create an index on an unsorted attribute, then that would be secondary index instead of primary. And what's the difference between the two? In secondary index we will be having an index record corresponding to every single record in the original file. So in original file we are having 1,50,000 records, and for each one of them there would be a corresponding entry in the index record file as well. So now here another thing they are mentioning is that assume that the record of data file and the index file are not split across the disk blocks, which means one single record is not spread across two different blocks, it is accommodated in just a single block, and this suggests us that it is an unspanned strategy used over there. And given these conditions, the number of blocks in that index file has to be found out. So first of all, we'll be starting with an index record. What will that index record consist of? They have already mentioned that each student record has a candidate key attribute of size 12 bytes, which means we have a key value pair, and in that the key will be this candidate key attribute enum, which is having a size of 12 bytes, and along with that there will be a record pointer whose size is given as 7 bytes. Hence in total that would give 19 bytes, which means every index record is having a size of 19 bytes. And in this case, what's the number of blocks we will be needing in order to store these index records? That would be given as the total number of blocks, which is 4096 divided by 19. And here we will be taking the floor function because it is an unspanned strategy. So if there is any residual record left out, then it will have to go into the next block and it cannot be accommodated in the existing one. So when we calculate this thing, we will be getting the floor of 4096. Can calculate that, and it turns out to be here we have 4096 divided by 19, which is 215 point something, and we are taking the floor function, so it will be simply taken as 215. So this is the number of blocks we will be needing for the index records, and in total what's the number of blocks that index file will be having. So for that, what we'll do is this R 1,50,000, that is the total number of records in our original database file. So corresponding to that, if we are having 215 index records in one single block, then the total number of blocks that we will need is that 1,50,000 divided by 215. And this time we will be needing to take the ceil function instead of floor. And the reason behind this is that if there is any residual block left out, then that cannot be used for the next set of records. It will have to be left out blank. Hence we are taking the ceil function, so that when we take the division of this 1,50,000 divided by 215, that gives us 697 point something, and whatever is the block left out here, it cannot be used for the next database file. It will be left blank. And here we take the floor function. Here we took the ceil function. So this will be rounded off to become 698. That is the total number of blocks that our index file will be having. So the result of this question would be 698. Programming question. We have been given a C program and we have to determine what would be the output returned by that. So it is a recursive program. So let us try to create out the recursion tree for this. In the main function, we are calling this function foo with these parameters 15, 15 and 10. Now those arguments, when go into this function, then this x becomes, let us denote function f foo as f, and the initial parameters are 15, 15 and 10. So then we go into this function call, and which of these conditions satisfy? X less than 0, no. Y less than or equal to 0, no. Similarly, these two do not satisfy. So we go on to this step and we return function foo of x, which means 15, then y minus q, so 15 minus 10, 5, and this remains the same. So we return the sum of these two actually, and on this side x is decremented by q, so that becomes 5, rest to remain the same. So this is what we get after the first recursive call. Then what does this function do? Again, none of the conditions satisfy for this, so it will again return these two functions, 15 minus 10, so 5, 5, 10 plus f of, now this time 15 will remain same, and this y will be decremented by q, this one. Y minus q means 5 minus 10, so minus 5 and 10. That is what it will return. Similarly for this one, again two function calls will be made. First one will be 5 minus 10, so minus 5, 15, 10, and next is 5 will remain the same, 15 minus 10, 5 and 10. So we have got these 4 recursive calls, and the values returned by all the 4 of them will be added together. Now looking at this first one, f of 5, 5 and 10, let us take that separately over here. Now in this one we can see again none of these conditions are satisfying, so again two more function calls will be made. The first one would be here 5 minus 10, so minus 5, 5, 10, and next one would be 5 minus 5, 10. Now for this one, if we check out, the value of x is less than or equal to 0, so that time this condition will be satisfied. And what does that return? It returns f of x remains the same, so -5, and only the y is decremented now. So that will give -5, 10. Similarly, for this one, the last condition will be satisfied, y is less than or equal to 0. So that will be returning f of x minus q. So 5 minus 10, -5, -5, and 10. Both of them are making the same function calls now. So what is the result of that? Now x and y are both negative. Hence, we'll go to this first condition. It is being satisfied and the value returned will be simply q. So both of these will return the value of q, which is 10. And the sum of that 10 plus 10, so this will be returning 20. So here this call returns 20, and that same call is again there at the end. That will also return 20. Now for these two calls, let us check out what are the function calls they are making. Here y is negative, so this condition is satisfied, only x will be decremented. So that will give us f of 5 minus 5, 10. Similarly, this will be f of -5, 15 minus 10, 5, and 10. Now as we can see, these calls are similar to the ones which we calculated below. This one matches to this because y is negative, and for this one x is negative, so this is the matching call. And as we just saw, both of them are returning the value of q, which is 10. So these two will also return the value of 10. So I've got the 4 values returned by all the 4 of these function calls, and all of them will be added to give the final answer. For this one, 20 plus 10, 30 will be returned. Similarly, for this one, 10 and 20 will give 30. So at the final first recursive call, the two values we have got is 30 and 30. So their sum, which is 60, that will be returned. Hence, the value which will be coming into this variable r will be 60, and we are simply printing that. So output of this program will also be 60. As a graph theory question, we have been given this directed graph, and for that we need to determine which of these 4 options is or are correct. The first one is saying the graph does not have a topological order. So now what do we mean by topological order, and in which graph does it exist? It only exists for the DAG or directed acyclic graphs. Is our graph directed? Yes, it is. But is it acyclic? It is not. We can see 2 cycles over here. This is a cycle, and in the same way we can see another cycle between these 4 nodes. So this graph is definitely not cyclic. So the topological order will not exist for this graph. And what did we mean by topological order? It is such an arrangement of nodes such that, let us say if we have such a graph, let us call the nodes as A, B, C, and this is D. Then for such a graph, it is directed and it is acyclic. So for this we can form a topological order such as we will be having A first, then after that, like we are dividing it into levels. After A we can have either B or C, both are allowed. So we can go with B and then C, and then these both together leads to D. So after B and C both are done, we will be having D. Another topological order will be A, C, B, D. That is also possible. So it is like an arrangement of nodes in the order in which the inputs are going into them, the incoming edges are going into those nodes. So that is what a topological order is, and it will not exist for the given graph. So option A is true. Now next one is saying that the depth first traversal starting at vertex S, this is our S, classifies 3 directed edges as back edges. Now what do we mean by the back edges? When we do a DFS traversal, then we will be encountering some nodes in such a way that they will be leading back to their ancestors. For example, if we have, let us consider these 4 nodes and there is a cycle between them. Then if I start my DFS at this particular node, then I'll go this way, this way, this way, And now while I'm at this particular node, it has only one outgoing edge, and where is it leading to? Its parent itself. So this edge will be classified as the back edge. We can visualize it properly if we construct a DFS tree out of it. Let us call these nodes as 1, 2, 3, 4. We started our DFS traversal at 1, then we went to 2, then we went to 3, and then 4. And from 4, where can we go? There is only one possibility, edge 4 to 1. But that edge is leading to its ancestor itself, because 1 is an ancestor of 4. So such an edge is called as a back edge. So in our graph, we have to perform DFS traversal and then check which are the back edges that we might encounter. So for simplicity, let us number the nodes so that it will be easy to identify. Okay, so let's do it this way. We can call these nodes as, starting from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. This S itself represents 13, that is our starting location. So from here we have to perform DFS on this graph. And alongside we will also keep constructing the DFS tree. So we are starting at node S or 13. From that there is only one outgoing edge, so we'll be visiting 14 after that. Now from this 14 we can go either to 10 or to 15. Let us go to 10 first. This way. Now from 10 we have 3 options. We can go to any one of them. Let us go to, let's say, 9. So from 10 to 9 there is an edge. Now from 9, because this was a cycle, 13, 14, 10 and 9, they are forming a cycle. So now from this 9, if we go to 5, that's allowed. But if we are going to 13 from 9, then 13 is its parent itself or the start node. So from 9 there is an edge which is possible leading to its parent. Not immediate parent, its ancestor. So this edge can be called to be a back edge from 9 to S. This is one back edge that we have found. Now from 9 we will not go to this way because it will be forming a cycle. So we will go to 5 from 9. So from 9 we went to 5. And now from 5 again we are having two choices. We can go either to 1 or to 6. Let us go to 1. So from 5 we went to 1. Now from 1 there is only one option. We can go to 2. From 2 we'll be going to 6. Now from 6 again we have only one option. We can go to 7. From the 7 we have two options. Either we can go to 3 or we can go to 8. Let us say we are going to 3. So from 7 we are going to 3. Now you can see that from this 3 we again have two options. We can go either to 2 or to 4. But this edge from 3 to 2 will again be forming a back edge because 2 is an ancestor of 3. And at this part, this is again a cycle. 3, 2, 6, 7. It is again forming a cycle. So there is a back edge from 3 to 2 as well. So we'll not be going to 2, we'll be going to 4 from 3. Now from this 4, we don't have any outgoing edge. So we'll be having to backtrack from there. So we'll come back to 7. And then from this 7, we will go to 8. From this 8, again there is no outgoing edge. We can only go to 4, that is visited already. So we'll again go back and do the backtracking. We can come back to 7. There is no outgoing edge left at it. So we'll again backtrack from 7. We are here right now at 7. From 7 we'll go to 6. Is there any other outgoing edge at 6? No. So we'll go to 2. From 2 there is again no option. From 1, no, it's not there. From 5 we could go to 6, but 6 is already visited, so there is no meaning doing that. So we'll go to 9, and from 9 is there any possibility? No. So we'll go to 10. Now from 10 we can go to 11, that is allowed. So we'll go this way from 10 to 11. Now From 11 we have only this outgoing edge, but that is already visited, so we will not go there. Instead, what we'll be doing is we'll follow this bottom path from 11 to 15. That is also an outgoing edge. So this way, and then from 15 we'll go to 16. Now at this 16 we can see there is only one outgoing edge, and that is leading to 12. So, and 12 is unvisited, so we'll go from 16 to 12. Now as you can see, from this 12 there are two outgoing edges, one is going to 8 and one is going to 11. But because this was a cycle, hence 11 is an ancestor of 12. 8 is not an ancestor of 12. So an edge from 12 to 11 will also form a back edge. An edge from 12 to 8 will not form. Anyways, both are already visited, will not be drawing that edge. But if it were there, then it would be called as a back edge. So yes, we got three back edges in this graph. And what were they? It was 9 to S, or you can say 9 to 13. Then it was 12 to 11, and then it was 3 to 2. There are three back edges, so this option is true. Now coming to C, the graph does not have a strongly connected component. We saw three different cycles in this graph, each of size 4, and each of these cycles represent a strongly connected component. So this graph does have the strongly connected components. That statement is incorrect. And coming to the last one, for each pair of vertices U and V, there exists a directed path from U to V. Now you can pick any two vertices and check it out for yourself. For example, if we take this top left as the source vertex and this bottom right as the destination vertex, then you can check that there is no path from the source to destination. From here you can go this way, this way, this way, and this way. Now you are stuck. There is no way we can reach this bottom right vertex. Similarly, you can check for any other pair of nodes and you will find out that no, there is no directed path existing between every two pair of nodes. And the reason for this is that the graph is not strongly connected. Hence, this statement D is also incorrect. The only correct answer is option A and B. Question is from the number systems. We have been given the single precision floating point representation of a real number as per IEEE 754 standards. It is like sign bit, exponent, and then mantissa bits. So we know that how do we perform IEEE 754 representation of floating point numbers? We have a 32-bit integer, sign, exponent, and mantissa. So we have 32-bit real number in which we represent it. Sign bit is 1 bit, then 8 for exponent, and remaining 23 for mantissa. This is a single precision, that's why it is 32-bit. Otherwise, in double precision, we go for 64 bits. So now for this representation, they are asking us which of the following choices is correct with respect to the smallest normalized positive number represented using the standard. So we want to represent the smallest possible positive number using this representation. So how do we represent numbers using this? It is normalized form. So we'll go for implicit normalization like -1 raised to the sign bit, then 1 point mantissa, means whatever bits are there in the mantissa, we place them over here. Then we do 2 to the power of exponent minus the bias. The bias we generally go for is 127. So this is how we represent the numbers using this representation. So if we were to find out the smallest possible positive number, then what would be the values of exponent and the mantissa? That is to be found out. Now we know that if we have exponent as all zeros, means 8 zeros are there in the exponent, and in mantissa part we have all zeros again, then this represents a 0. And instead, if we have all ones in the exponent and all zeros in the mantissa part, then that represents infinity, either plus or minus infinity depending upon your sign bit. So both of these choices are excluded. Then how will we represent the smallest positive number? Let us check the options. Exponent is all zeros, mantissa is all zeros. So we just discarded it being 0. Next is exponent is all zeros, mantissa is 1 at the rightmost end. But as you know, how do we place the bits in the mantissa? They are placed from this left to right side. The leftmost bit has the smallest weight. If this mantissa has to be placed over here, it would be 1.000, so on, 22 zeros followed by this 1. So in order to reach this one, you will have to multiply it with 2 to the power 22 or 23 in order to skip all these places and come over here. So this is definitely not going to be a smallest positive number. Third one is exponent is 1, mantissa is all zeros. So this seems to be a possible candidate for the answer. And similarly, going for the last one, exponent is 1, mantissa is again 1 at the right end. So we'll definitely discard this one because we cannot skip these many decimal points to reach that one. It will definitely not give the smallest positive. So again, this one is discarded. We are just left with option C, which is 1 in the exponent and all zeros in the mantissa. Let us check what number does it actually represent. So let us erase this and write that here. Using the implicit notation itself, the number which this C option will represent is, the sign bit is not given, so we'll assume it to be positive number, because anyway we have to get the positive number, so it has to be 1 itself. So that part is skipped. We'll go for 1.m. What is mantissa here? All zeros. So we can write just 1 0, doesn't matter, into 2 to the power. Now exponent is just a 1. And we will add to it the bias of 127. So it will be 1 minus 127. So that becomes 1.0 into 2 to the power minus 126. Or this is 0 after the decimal point, so we can simply skip this part and write it as 2 to the power minus 126. So this is the smallest positive number we can represent in this number format. So the correct answer would be C. The smallest positive number represented in the standard is denoted by option C. This is an algorithms question based on recurrence relations. We are performing a recursive binary search on a sorted array of size n. This is a recursive binary search, so it will be using the divide and conquer approach, and we have to determine the worst case number of arithmetic operations that will be involved in performing this operation. So let us say f of n is the total number of operations that we will be requiring, and every time what do? We divide the problem into two sub-problems. For example, if we have this array, then we'll go to its middle index, and then depending upon if it is the required value which we have to search or not, we will go either to the right or to the left. We'll go for one of the two parts. So what we're doing, we are dividing the problem into two parts and then going into one of them. If let us say the number we are searching is 3 and the middle element we have got is 5, so we are sure that we need to go in the left part. So we divide a problem into two parts and go in only one of the two parts. The next part will be discarded. We don't evaluate it. So this is how the recurrence relation can be formed in some constant operation for doing this comparison and everything. So this is how the recurrence relation can be given for this problem. So now this f of n represents the total number of operations that we require. So if we solve this recurrence relation completely, then we'll be able to tell what is the asymptotically number of equations we are requiring. You can generalize that. So there are multiple ways to solve this recurrence relations now. We can either form a recurrence tree, or we can go for mathematical substitutions, and Master's theorem is also applicable. Let us say if we try to convert this problem into Master's theorem, then its general term, which is T of n equal to a times T of n by b plus theta of n to the power k log p n. Then for this case it becomes a is 1, b is 2, k is 0, p is 0, because it is simply one constant operation. So here a is equal to b to the power k, 1 equivalent to 2 to the power 0. So this goes into the case 2 of the Master's theorem. And the value of p is also 0, which is greater than minus 1. So this goes to case 2.1, and it will be evaluated like T of n, or in this case f of n, equal to theta of n to the power log a to the base b into log of p plus 1 n. So this becomes theta of a into the power. What is log of a? In this case, it will be log of 1 to the base 2. And log 1 is 0. So this becomes n to the power 0 times of log p plus 1, and p is 0, so p plus 1 is 1. So log 1, we can eliminate that 1, and n. N to the power 0 is again 1. So this becomes theta of log n, and the base of this logarithm will be 2. So we get theta of log n to the base 2 as the total number of arithmetic operations required by this recursive binary search. And this is how we'll also give the time complexity, because time complexity is directly proportional to the number of operations we are performing. So this is what will be the number of operations required, or you can say the time complexity for performing a recursive binary search in a sorted array of size n. Even if we go for the iterative version, it turns out to be the same. So option B is true. This is a digital logics question based upon combinational circuit. We have been given a circuit, 4 circuits actually, and from that we need to determine which of them is correctly implementing the given function f. It is having 3 variables x, y, and z, and it is denoted using these minterms. So let us first check out what is the function we are actually looking for, and then we shall look at the options that which of them can implement that correctly. So this is a function of 3 variables, so we can evaluate it using this K-map. Let us put the variables x and y over here. Here goes z, 0, 1, 0, 0, 0, 1, 1, 1, and 1, 0. Now the first minterm is m0. For that, this will be the corresponding cell. We'll be putting it 1. Next comes m1, so it will be 0, 0, 1. So the corresponding cell is this. For m3, it will be 0, 1, 1, this cell. m4, 1, 0, 0. m5, 1, 0, 1, and m6, 1, 1, 0. So these are all the cells we have filled up using the minterms. Now it is evaluated. We can combine these 4 as a size 4 minterm. Then these two ones cannot be combined among themselves, so we'll just make 2 terms like this. Now when we go on to evaluate this, it will become, for the size 4, we will be getting y bar plus, now this minterm is going to give us x z bar, and then this one is giving us x bar z. So this is the expression we are looking for. So now we have to check all the multiplexers and see which of them can give us this output. So now for this we need to know how to evaluate the output of a 4x1 multiplexer. If we have a mux like this, S0 and S1 are the signal bits, and let us say PQ, RS are its inputs. Then how do we evaluate it? It is done as S0 bar S1 bar P plus S0 bar S1 Q plus S0 S1 bar R plus S0 S1 S. This is how we evaluate a 4x1 multiplexers, which means we are taking all the combinations of S0 and S1, just the way we fill the truth table. And along with that, each of these 4 inputs are ANDed. So now let us evaluate the given options and check which of them can give us the same result. Now looking at the option A, its signal bits are Y and Z. So the output will be evaluated as Y bar Z bar, the first input which is 1, plus Y bar Z, second input which is 1 again, plus Y Z bar, the third input which is X, plus YZ, and the last input which is X bar. Let us simplify this. It is Y bar Z bar plus Y bar Z plus X Y Z bar plus X bar YZ. Now we can combine these first 2 terms together. After taking Y bar as common, this Z bar and Z will add up to 1. So there is no need to write that. Plus, now from the last 2 terms, we can take Y common, and that becomes X Z bar plus X bar Z. Now we can again apply distributive property over this, because this is Y bar and Y. So after applying the property, it will actually become Y bar plus Y, Y bar plus the remaining bracket, x z bar plus x bar z. Now this y bar plus y will again give us 1. So what we are left with? Y bar plus x z bar plus x bar z, and this is what we wanted as the output. So this first option is correctly implementing the required expression. We can also check for the other three options, but this is a MCQ type question. There is only one answer correct. So we will be going with option A because it is correctly implementing the given function. So A is the correct answer. This is a DBMS question based upon transactions. We have a schedule with 3 transactions, T1, T2 and T3 in a relational database system given as follows. We can convert them into the representable format like this. These are the 3 transactions and they are performing read and write operations on the variables x, y and z. The first operation we are performing is read operation on y by transaction T2. So we can write that over here. Next we have read operation on x by transaction T1. After that read on z by T3. Then next we have read on y by T1. Next is write operation on variable x again by transaction T1. Then read operation on z by transaction T2. Then write on y followed by the last 2 operations by transaction T3, which are read on x and write on z. So now we need to determine whether this is conflict serializable schedule or not. So for that we will mark down the dependencies among this, such as the read write dependency or write write dependency among the same variable. So here if we see, this is read operation on x and there is no write operation on x in either T2 or T3. So this will not cause any conflict. Then in T1 we have a read operation on y and in T2 we have a write operation on y. So this is causing a read write conflict. We can alongside draw the dependency graph as well. And as we saw, there is a dependency from T1 to T2, so this edge will be made like this. Then any other dependencies, here there is a write operation on x and T3 has a read operation on x, so this will also cause a read write dependency. So from T1 to T3 will also there will be a link in this graph. Then in T2 read operation on y and there is no write in T1 neither in T3, so it is not causing any conflict. Then this read operation on z and the write operation on z by T3, that causes a conflict, so there will be an edge from T2 to T3. Then this one we have already covered, read 3 on z and read 2 on z, there is no conflict between read and read operations, and these two are already covered. So these are all the conflicts which we had, and as we can see in this dependency graph, if we try to make its topological sorting, then it will be like T1 will be performed first because there is no incoming edge to it. Then after T1 we can perform either T2 or T3, but because there is an edge from T2 to T3, so we need to perform T2 next, and after that we can have T3. So this is an equivalent conflict serializable schedule for the given schedule. So it is definitely conflict serializable. Statement P is correct. What Q is saying is if T3 commits before T1 finishes, then S will be recoverable. Now we are not concerned if it is recoverable currently or not. If this thing happens, then will it be recoverable? That we need to determine. Now here we can see T3 is performing read operation on X, while T1 is doing a write operation on X before that. Similarly, it is performing a write operation on Z and it had read that earlier, so there is no conflict for Z. But since it is reading a value written by T1, so T3 needs to commit after T1. If T3 commits before T1 itself, then the schedule will not be recoverable. So statement Q is incorrect. So So we will be going with option B, which is saying P is true while Q is false. So that is the correct answer. This is a COA question from cache memory. We have a set associative cache of size 2 KB. Let us note that down. The cache size C is 2 KB, which means 2 times of 2 to the power 10 bytes or 2 to the power 11 bytes. And in this cache, the block size is 64 bytes. So we can say the block size B is 64 bytes or 2 to the power 6 bytes. Now they're saying that the cache is byte addressable and it is taking a 32-bit address, which means this is the cache addressing format. First we have the tag bits. After that there is a set index, and finally we have the block offset. And in total these three fields are taking 32 bits, which we call as the physical address of the cache. And now they're saying the width of the tag field is 22 bits. So width of this tag field is already given as 22, and using this block size we can calculate the block offset, because the block size is 2 to the power 6 bytes, hence the offset will be 6 bits in length. So this offset is 6 bits. And now from 32, this is 22 and that is 6. So the set index will be taking 32 minus 22 minus 6, which is 4 bits. So we get the set index as 4 bits. And what does that imply? That the number of sets we will be having is 2 to the power 4 or 16. But what do we want to calculate? The associativity of the cache. And how will we get that? For that we need to calculate what's the number of cache blocks we are having. And how do we get the number of blocks? By cache size upon block size. And cache size is given as 2 to the power 11 bytes. And block size we know is 2 to the power 6 bytes. And hence that gives us 2 to the power 11 minus 6 equal to 5, that is 32. Which means in total we are having 32 cache blocks and 16 cache sets. And what does this imply? That every set will be having 2 blocks. 32 blocks and 16 sets, which means the associativity will be 32 by 16 equal to 2. And that implies that every set is having 2 cache blocks. So associativity for the given cache will be 2, and that is our answer. This is an algorithms question based upon asymptotic notations. We are having the constants a and b, where a is greater than or equal to 1, b is greater than 1, and we have been given this particular recurrence relation that has been defined on the non-negative integers. So for this we have to determine which of these options is or are true about its complexity. The asymptotic notations have been given. So now for this recurrence relation, it has to be modeled using the master's theorem, and using that we have these 3 rules that will help us compute its complexity. But if we have a look at the options in a and b, we can straight away have a look at that here f of n is n log n to the base 2, and here it is n divided by log n to the base 2. So in both of these cases we can see that the result is independent of a and b, which cannot be possible. The condition on f can never be independent of a and b for whatever cases we deal with. So these two can be straight away rejected. And then coming to c and d, we will need to take help of these 3 rules which have been derived using master's theorem itself. For option c, we can see that it matches with this case 1, and for this, as we know, the complexity has been derived as theta of n raised to log a to the base b, and that is what it has been given over here as well. So we'll say that option c is definitely true. In the same way, when coming to the last one, it is f of n has been conditioned as theta of n raised to log a to the base b, so that maps with this case 2. And for this, using the master's theorem, we can evaluate its complexity or the recurrence relation t of n as theta of n raised to log a to the base b and along with that this log n has to be added. That has not been given over here. So again, the given relation over here in terms of t of n is also incorrect. So option D is also rejected and we get only C as our answer. Engineering mathematics question. We have been given a function f which is continuous in the closed interval -3 to 3 and differentiable in the open interval -3 to 3, such that for every x in this interval, f dash of x, which means the differentiation of x, is less than or equal to 2 and f of -3 has been given as 7. So now using all these conditions, we have to find out what is the maximum possible value of f of 3. So now there can be two possible methods to solve this. First one would be to assume f of x to be a polynomial function, maybe a linear one, and then try to substitute both these values and manipulate it. And to find out the maximum value, where do we find the maximum value? At the critical points. So that can be visualized, but the better way, more accurate one, would be to use the mean value theorem. Our function f is continuous in this closed interval and it is differentiable in this open interval. So it is a valid candidate to be applied the MVT in this range. Let us call this range as the bounds as a and b. So within this range, we can say that there will be a point C such that f of C can be given as f of b minus f of a upon b minus a. So there exists some point C at which the differentiation of this function, which is f dash of C, can be given as this particular expression. Now our a is -3 and our b is +3. They are the bounds of our interval. So this expression actually becomes f of 3 minus f of -3 upon 3 minus of -3. So 3 plus 3. Now we already know that the value of f of -3 is 7 and the denominator here is 6. So we get 6 times f dash of c equal to f of 3 minus 7, and we can say f of 3 equal to 7 plus 6 times f dash of c. Now we know the value of f dash of x to be less than or equal to 2. So x is also a point in this interval and c is also a point in the same interval. So we can use this particular value of f dash x in place of this f dash of c, and that will give us f of 3 equal to, now this value f dash of c is less than or equal to 2. So because of this inequality, even this equality will change into an inequality. So we will say that f of 3 is less than or equal to 7 plus 6 times of 2, and this becomes 7 plus 12 equal to 19. So we say f of 3 is less than or equal to 19, which means what is the maximum possible value of f of 3? 19 itself. So we get max value of f of 3 equal to 19. So the answer for this question will be 19 itself. As a compiler design question, we have been given a C code, and in that we are assuming a structure which has been allocated from the heap. It contains two fields f1 and f2, and that is the reason why we are having this y referencing f1 and y referencing f2 as the dereferencing operations, because that is the dynamic memory allocated from the heap and we are dereferencing it. So that is a pointer dereferencing, and we are having the local variables x, y, z, p, q, I. They are stored in the registers, and we are applying the common sub-expression elimination CSC optimization technique on this code. So in the resulting code after the optimization, what will be the number of addition and the dereference operations which we just discussed will be present respectively has to be determined. So in this particular code we can see there is a for loop which is running up to from 0 up to 200, but it is getting incremented by 2 every time. So in effect it will run just for 100 times. And inside that loop we are having these addition plus dereferencing, addition plus dereferencing, and two addition. Those operations are present inside it. But right now, as we can see, there is a lot of redundancy in this. We can optimize this code to result into something like, we can say T1 equal to, let us have a look at this initializer statement. In this we can say T1 is y referencing F1. So here every time when we see this y referencing F1, we can simply replace it with this T1, and this value is not getting manipulated further in the code. So if we calculate it just for once and store it, then it can be used multiple times without again requiring us to do the dereference operation. Then in the same way we can store this y referencing F2, and that can be used in this place. Similarly, we can see this x plus 3 is also redundant code. It can be seen at these two places. So we can further store that in a variable. So now our variable z will become T3 in place of this x plus 3. Then here it will be T1, and at the last it will be replaced with T2. So this is this line 1 we have modified, and now entering into the loop it will be for I equal to 0, I less than 200, I plus equal to 2. Now inside this loop we will be going either into the if part or into the else part, depending upon which one gets satisfied. When we go into the if part, then what we'll be doing is p equal to p plus x plus 3, which means T3, and q equal to q plus y referencing F1 means T1. Either these two operations will be performed, or in the else part we'll be performing p equal to p plus y referencing F2, which means T2, and q equal to q plus T3. This is what our optimized code will look like. Now in this code we can see what is the number of dereference operations. 1, 2. Is there any other dereference operation we can see? No. Inside the loop we have not used any. So there are only 2 dereference operations left in our optimized code. In the same way, now let us calculate the number of addition operations. Here we can see 1, 2, 3. Outside the loop we got 3. Now let us move inside the loop. Now in this loop, as we just discussed, either the if part will be executed or the else part will be executed at a time. If the if part gets executed, then we are having 1 and 2 addition operations. If we go to the else part, then again 1 and 2. So in every iteration of the loop we will be performing only 2 addition operations, and the loop is running for 100 times, and we are performing the addition operation 2 times each, so that becomes 200. But now, as you can see over here, this I plus equal to 2, the value of I is being incremented after each iteration, and this is also an addition operation to be counted. Now the loop is running for 100 times, hence this particular operation will also take place 100 times. These both will also take place 100 times. Any one of them at a time, but collectively both of them will be 100 times. So what is the resulting number of addition operations we got? We have got 100 for this, and then these two combinedly will run for 100 times. At a time, any one of them will run. So in total, from this we will be getting 200 operations. From here we got 100. So in total we have 300 plus outside the loop we got 1, 2 and 3. So 300 plus 3. So 303 addition and 2 dereferencing. This is the number of operations we will be having in the optimized code. Once again, let us have a look. How did we get 300? 100 for this increment operation and 100 times any one of these two conditions will run, either the if part or the else part. Let us say 50 times if is satisfied and remaining 50 times else is satisfied, which means 50 times we will be performing these two operations and remaining 50 times we will be performing these two operations. So whatever is the distribution, as a result we are going to get 100 times 2 operations, which is 200 operations from this. So this 100 plus 200 from this if else gave us 300, and there are 3 outside the loop, so 303. Hence our correct answer for this question is D. This is a COA question. We are having a computer system with DMA support, and this DMA module is transferring one 8-bit character in every CPU cycle from device to memory, and the mode used here is cycle stealing mode. So the speed of the processor has been given as 2 MHz, which means in 1 second the number of cycles we will be having is 2 times of 10 to the power 6, and out of these 0.5% cycles are being stolen and used for the DMA purpose. So what is the number of cycles being used for DMA? 0.5%, which means 0.5 by 100 times of 2 to the power 2 times of 10 to the power 6. That gives us, this is 10 to the power 4, so 5 to 10 to the power 3, that becomes 10 to the power 4 or 10,000. So in total 10,000 cycles are being stolen for DMA, and in each of these cycles we are transferring an 8-bit character. So the data transfer rate per second has to be found out. This is the 1 second only we are dealing with. Now in every second, what's the data amount of data we are transferring? That would be 8 times of 10 to the power 4. So that becomes 80,000 bits. So this is the amount of data we are transferring in 1 second. Hence the data transfer rate for this device would become 80,000 bits per second. Hence the answer for this question will be 80,000. This is a C programming question. We have been given a code and we need to determine what will be the output printed by that. So let us see what this code is doing. It is declaring a 4x5, which is a 2-dimensional array, ARR. So that array will be something like this. It is having 4 rows and 5 columns. So we can make it this way: 1, 2, 3, 4 and 5. The indexes will be 0, 1, 2, 3 and 0, 1, 2, 3, 4 respectively. So this is our array. Now what they are doing is they are looping over this array using 2 for loops. They are traversing each and every element and they are initializing it using 10 times I plus j, which means 10 times the row value plus the column value. These are our I indexes, these are our j indices. So let us fill the entire array and then let us determine what will be the output printed. So for this first index 0, 0, it will be 10 times of 0 plus 0, which is 0. Then in this entire first row, the value of this 10 times of I will be same because I is not changing, only j is changing. So for the entire first row, 10 times of I will give us 0, and to that we are adding the j value. So it will simply be 0, 1, 2, 3 and 4. Now for this second row, 10 times of I will give us 10. Now to that 10, we will be adding these 0, 1, 2, 3 and 4. So it will be 10, 11, 12, 13 and 14. Similarly, for I equal to 2, this value will be fixed as 20, and to that we will be adding the j value. So that will give 20, 21, 22, 23 and 24. Then similarly for this last row, that will give us 30, 31, 32, 33 and 34. Now we have created this entire matrix and we need to determine the output of this address star of array of 1 plus 9, which means array of 1 will take us to this first row of this matrix, and to that we are adding the offset as 9, which means we have to move 9 steps ahead from this particular address. So this is our array of 1. From this, if we move 9 steps ahead, it will give us, this is step 1, 2, 3, 4, 5, 6, 7, 8 and 9. So we have reached this element 24. Why did we move to 20 from 14? Because they are stored in the contiguous memory location. We can assume that they are stored in the row order fashion. So after this first row is completed, we will go to the next address, which would be at 20. So from the given address, which was the address of this 10 array of 1, it was the address of this 10 actually, and from that if we move 9 steps ahead in this contiguous manner, we reach this element 24, and we are dereferencing that address using this operator. So the value printed will be the value stored at this particular location, which is 24. So the output printed for this code will be 24. Programming question. We have been given a C code and we need to determine what is the value returned by the function call with values 15 and 225 as the parameters. So let us take a smaller example and understand that. Let us call the function as f and let the parameters be 10 and 35. Let us see what this function does. The first one is x, second parameter is y. None of them is 1, so this is not satisfied. They are not equal. This is not satisfied, so we go to here, y is greater than x. If this holds true, then what do? We recursively call the same function with parameters. First one, the smaller parameter remains the same, and second parameter changes to y minus x, which means 35 minus 10, 25. And in the next iteration, same thing will happen again. It will recursively call 10, 15. Next time again 10 and 5. This function call will be made. And now when this function call is made, we can see that this condition satisfies. X is greater than y now. So in this case, what is the recursive call we do? X minus y and y, which means every time whichever is the larger parameter, from that we subtract the smaller one. So this will give us f of 10 minus 5, which is 5. The smaller parameter remains the same. And now when this function call is performed, the second condition is satisfied. X is equal to y, then x is returned. We can return either x or y because both are same in this case. So this will return us 5. And hence the recursive call which we had initially made, f of 10, 35 will return us 5. And as we can see, for 10 and 35, 5 is the GCD. So what this function is basically doing is, it is giving us the GCD of two numbers using repeated subtraction. Whichever is the larger number, we are converting it into larger minus smaller, and the smaller number remains the same. So in this way, we are repeatedly subtracting the smaller number from the larger one, and ultimately we will reach the GCD. And if both of them do not have any common divisor, then we will go to this first condition and 1 will be returned. So this is GCD using repeated subtraction. In general, how do we calculate GCD? Instead of subtraction, we go for modulo. For 10 and 35, how do we calculate GCD? We will go for 10, 35 modulo 10, which is 5. And in the next call, what we'll do? Here we can say that 10 divides 5. So the lower of them, 5, will be returned as the GCD. That is the method which we generally go for, but this is performing division instead of repeated subtraction. So if we are calling the function on 15 and 255, their GCD will be returned. And as we know, GCD of 15 and 255 will be 15 itself, because 255 divides 15. So the answer of this question will be 15. Engineering mathematics question based on vectors and matrices. We are having two n-dimensional real vectors p and q such that an operation s has been defined on them, which is given as s of p and q is sigma of p of I dot q of I. So this operation is nothing but the dot product of two vectors. And for every possible pair of P and Q, we'll be performing this operation on every dimension, one at a time. It is an n-dimensional space. So from I going from 1 to n means in every dimension, we are taking the dot product and then we are summing them up. So given this operation, we are having a set L, which is a set of 10-dimensional non-zero real vectors, which basically means that we are having a 10-dimensional space, and for that there are corresponding vectors in that, such that for every pair of distinct vectors P and Q in this space L, which means from this 10-dimensional space L, in which we are having a set of those 10 non-zero real vectors, we are taking up two vectors at a time represented as P and Q, such that their operation S of P and Q gives 0. Now S is nothing but a dot product, as we just saw. So when do we get the dot product of two vectors are 0? When they are mutually perpendicular. So from this 10-dimensional space, from those 10 vectors, we are picking up two vectors at a time such that they are mutually perpendicular. So basically we need to find the number of such mutually perpendicular pairs which are possible. And what's the maximum cardinality for this set L? That would be the same. If we are having a 10-dimensional space, then there would be 10 different ways in which we'll make such combinations possible, and those 10 vectors taken up two at a time will be forming the mutually perpendicular pairs. So in the resulting set L, its cardinality would actually represent the number of such mutually perpendicular vectors we could find out, and that is, as we just saw, is 10. Hence cardinality for this set has to be 10. That is our answer. This one is a DBMS question about relational data model and the foreign keys. We have two statements and need to determine which of them is or are correct. The statement S1 is saying that a relational scheme can have at most one foreign key. Is that correct? No, we can have any number of foreign keys in a single relation. For example, we can consider a relational scheme such as there are people and they are buying cars. So we can have a customer table which will have customer ID and they are buying cars. So cars table, in that we will also have, let's say, car ID. And now to determine which customer is buying which car, we can maintain a record in a separate table. Let us call it buys table. It will have the entries of customer and the car which they bought. So this CID is the customer ID referring to the customer table, and this car ID is the foreign key referring to this car ID in the cars table. So this buys relation itself is having two different foreign keys. In the same way, we can have any number of foreign keys in a relation. There is no restriction on its number. So the first statement is incorrect. Looking at the next one, a foreign key in a relation scheme R cannot be used to refer to tuples of R, which means it is trying to say that in the relation R, we cannot have a foreign key referring to some tuple of R itself. No, it is incorrect, because we have self-referential foreign keys as well. See, this foreign key is defined on an attribute. And what does that do? Foreign key tells us that in the attribute, whichever we have referred to, we can have only those particular values which are already present. Just for example, in this buy table, we will have these CIDs. And where are these CIDs coming from? From the customer table. So if it is having only the CIDs, say 1 and 2. So this buys table cannot have a CID 3. Because it was not present in its parent table. You can call it an inheritance type of thing. If that is not present in its parent table, then how did it come here? If there is no customer with CID 3, then how can someone with a CID 3 buy a car? So this foreign key constraint or the referential integrity constraint tells us that it is implemented on some of the attribute, and it tells us that whatever tuples we will be having in this particular relation will all be present in the original table. All those tuples, all those corresponding values will already be present. Otherwise, we cannot have them. So this statement is saying that we cannot refer to the tuples of the same relation from which we have referred. So for this we can have a counter example such as this is an employee table. It is having EID column and MID column, means employee ID and the manager ID. For which employee we are having which manager. Let us say employee 1 and 2 both are having the manager as 3, and then there is no manager for 3. Let us say C is the top level person in the company. So because we cannot keep this as empty, so we'll say 3 is the manager of itself. So now we can say this MID because every employee is also manager. So this MID is a foreign key referring to EID in the same relation. So we can have self-referential foreign keys which act on some attribute of the same relation, and it refers to the tuples, saying that all of these tuples, all of these values have to be already present from the attribute which we have referred to. Hence, the statement is also incorrect. So we will be going with option B. Both S1 and S2 are false. Engineering mathematics question based on probability. We are having a bag that has R red balls and B black balls. Initial configuration is given as R and B. R represents the number of red balls and B represents number of black balls. Now all of these balls are identical except for their color, which means all the red balls are identical and all the black balls are identical. Now in a trial, a ball is randomly drawn from the bag, its color is noted and it is placed back into the bag along with another ball of the same color, which means if you are drawing red in the first draw, then you will be placing back that red ball along with one other red ball, similar red ball. So after that operation, the bag will have R plus 1 red balls and black will remain the same. The number of balls in the bag will increase by 1 after the trial. Now the sequence of 4 such trials is conducted, and after that we are having to find out the probability that a red ball will be drawn in that 4th trial. So here we can go on to construct a tree for this. We'll be starting with a bag whose initial configuration is R and B. Now there are 2 cases. In the first trial, let us say we are drawing a red ball. So after that, the configuration would be R plus 1 and B, because the red ball will increase. And if we had drawn B in the first trial, then result would be R and B plus 1. So this was our first trial. Now going to the second trial, both of these will be branching out into 2. This will also have 2 outcomes. Here again R and B. If we are drawing R, then it would be R plus 2 and B. Here it will be R plus 1, B plus 1. Similarly here if we are drawing R and B, then R plus 1, B plus 1, R, B plus 2. So this was the second trial. Now moving on to the third trial, again each of these will have 2 more options. This one will give R plus 3, B, R plus 2, B plus 1, and in the same way each of these will also have 2 more configurations. That is the third trial. Now we have to find out the probability of drawing a red ball in the 4th trial. So let us say we are getting some outputs in each of these cases. Now when we move to the 4th trial, then we only have to find out the red probability from all of them. We are not concerned with blue. So this is how from each of these we'll again move on to the 4th trial, and in that one we will only consider the outcome of drawing out a red ball. And after we get the values in this particular level of the tree, then what we are supposed to do is we simply have to add out all of the 8 combinations. We'll get 1, 2, 3, 4, 5, 6, 7 and 8. So we'll be needing to add the outcome of all of these 8 branches. And how will we do that? Let us check out for that this first branch, the most extreme branch. Here the result of the last state would be R plus 4 and B. So for this branch, what we'll do is, in the first time, what was the probability of drawing red? It was R upon R plus B, because initial configuration was R plus B balls, and out of that we draw a red ball. So this was it for the first trial. Then in the second trial, this was the configuration, and from that we had to draw a red ball. So it would be R plus 1 upon R plus 1 plus B. This is the total number of balls, and from that we had to draw a red ball, and there were R plus 1 of them. So that would be probability. Then moving on to the third trial, it will be R plus 3 upon R plus 3 plus B. Then the fourth trial, it will be R plus 4 upon R plus 4 plus B. So this is the probability we got for this first branch, this first one, and same thing we have to repeat for all of these 8. And then we'll be adding the result of all of these 8 branches. That will be our resulting probability. And after doing that, it will turn out to be R upon R plus B. Once we calculate all the branches, then it would be easier, because most of the things would be taken out as common, and it would be easy to simplify, just that it is a bit lengthy to reach up to all of those levels and add them up. So it is a little time consuming, but not that difficult. We'll be simply getting the answer after simplification as R upon R plus B. So the answer for this question would be A. First question, we have been given these 2 statements about regular languages, and we need to identify which of these statements is or are correct. The first one is saying that every infinite regular language contains an undecidable language as its subset. For this, it would be better if we take some counter example and try to prove it. Let us say L is some regular language given by A star, or you can say sigma star, can also take A plus B, closure, anything. We are just concerned with taking some regular language, and then we'll try to prove if it is possible to find out any undecidable language as its subset. So we may come up with some language in which, let us say this is the language we are considering, and L1 is another language consisting of strings such as a raised to n, where this n cannot be generated using any algorithm. N is not any prime number. It is simply a number which cannot be generated by any algorithm. So we can say that there would be some sequence of numbers, let us say 4, after that 69, then 123, something like that. A sequence of numbers which cannot be generated using any existing algorithms. We can say it is randomly chosen or something like that, in such a way that it's not really possible to actually come up with an exact algorithm to represent this language. So this L1 will then become an undecidable language, and it is definitely a subset of this language L, which was regular. In the same way, we can also come up with some other languages, and even if it is not possible for us to actually come up with a language there, but we can say one thing for sure, that if L is a language with a regular expression as A star, then it has any number of A's including 0. So out of that, we can definitely come up with some language which would not be possible for us to express mathematically. Or if we consider this one, then it would be possible for us to come up with such a sequence of A's and B's which cannot be easily generated using any existing algorithm. And in such cases, those languages become undecidable. So it's definitely possible to have a regular language which would have undecidable language as its subset. So this becomes true. Now coming to the next one, every finite language is regular. Now this one is easier to prove. Let us say M is some language consisting of a finite set of strings W1, W2 and W3. So is it possible for us to come up with a regular expression for this? We can simply say that the regular expression for M would be W1 plus W2 plus W3. We can select any one of them. This is the regular expression itself for the language M, and it can definitely be represented by a finite automata if we have been able to come up with a regular expression for it. Hence, every finite language is also regular. We can definitely draw an automata for that. Maybe it will require infinite number of states or a large number of states, but it would definitely be possible to come up with it. So every finite language is definitely regular, and hence both of these statements are true. The correct option would be C. This is a compiler design question. They're asking that in the context of compilers, which of these options is or are not an intermediate representation of the source program. It is an MSQ type of question regarding intermediate code generation, which we know ICG is a step in compiler design in which we use the different representations of the source program, which are like 3 address code. Then we have the DAG directed acyclic graphs. Along with that, we have the postfix notation, and this DAG is derived from the syntax tree, so that is also a kind of representation of the source program. And out of these, we have the 3 address code, that is true. Abstract syntax tree, it is a condensed version of the syntax tree itself, just like DAG. It tries to optimize that tree and to reduce the number of nodes in that tree to make it more abstract in the sense, and hence it is also part of the ICG. Apart from that, the third one, which is control flow graphs, it's actually a step which we use in the optimization phase, the code optimization phase of the compiler design, in which what we do is there is a graphical representation of the source program in the form of the blocks. We can say these are the basic blocks B1, B2 and so on, and those can be mapped with a graph as when one basic block is complete, then we go into the next node. So that is how it is said to be a graphical representation of the intermediate code itself, as it has been mentioned in the reference book Ullman. And hence all of these 3 would be considered to be the intermediate representation of source program. The only one left out, which is symbol table, as we know, it is actually a data structure and not as a representation of a source program. This is used in all the phases of compiler, starting from the first phase and then going to linking, loading, and so on. In the syntax analyzing phase, then in semantic analyzing phase, even in the code optimization, all of these states make use of the symbol table to store information regarding whatever the new variables and the new symbols are encountered. Their entries are made into the table, then they are fetched back from it. So basically it's a data structure for storing information, and it is not a source program representation. So that would be out of these 3, it's not matching with them, and hence we would say that the symbol table is not an intermediate representation of the source program. So this D would be our answer. This is a digital logics question based on number system representations. We are having a 2-byte unsigned integer that is being represented on 2 different computers, in which one is following the Little Endian format while another one is following this Big Endian format. And what they're saying, the numerical value of that integer on Little Endian is 255 more than that on the Big Endian computer. So first let us understand what do we mean by this Little Endian and Big Endian. Let us say we have this integer ABCD. Let us consider only 1-byte integer. So these are 4 bits, 4 separate bytes making up an integer. So if it is represented on a Little Endian and Big Endian, how would it look like? We know that in the Little Endian, the most significant byte, which means this A, that would get the lower address, which means it would come on the rightmost extreme. So this number would be represented as A, B, C and D from right to left. The MSB gets the lower address, while in Big Endian it is in the usual format as we have. The MSB gets the highest address, so this number is from left to right. So that is how the representations differ, just in the way we read the integers from left to right or right to left. That is the only difference. But here they are saying that between these two numbers, which means if this DCBA is interpreted as a different integer itself, then this DCBA should be 255 more than the corresponding value of this ABCD. This particular property must be followed. That is what the question is saying. And now from the given options, we have to determine that which of these are the valid representations of unsigned integer on a Little Endian computer, which means considering these all options to be the corresponding Little Endian representations, we need to check if they are valid or not using this particular property, that the difference is 255. So how will we approach this? Let us first note down all these numbers in their corresponding Little Endian and Big Endian representations. So for the first one, Little Endian is given as 665. But another thing to note over here is the integers here are 2 byte unsigned integers, which means these 2 bytes put together, they would be considered in pairs. So we cannot simply reverse as we did for this number. It was ABCD, so we simply reversed it into DCBA in order to convert it from Big Endian to Little Endian or vice versa. Here we cannot simply reverse, we will need to reverse in pairs, just because integer is occupying 2 bytes. So for this, if this is the Little Endian, then we will have to reverse it to get the corresponding Big Endian, and that reversal would be done in pairs in this particular way. 65 will come first, all of them put together, they won't be separated, and then this 66 would come. So this is how the reversal takes place. So that is its corresponding Big Endian representation, 6566. Similarly for the next one, it is 0001. Again they will be reversed in pairs, giving 0100. For the third one, it's 4243, which would become 4342. The last one, that is 0100, becomes 0001. So now we have got the corresponding Little and Big Endian representations, but we don't know if all of them are valid or not. So how will we do that? We will check if their difference is coming out to be 255 or not. And all of these numbers are represented in the hexadecimal format. So their difference, this is actually in decimal itself. If we are considering the hexadecimal, then this 255 of decimal will correspond to FF in the hexadecimal. So we have to check if the difference comes out to be this FF or not. So let us subtract them one by one. The first one, that is 665 minus 6566. Let's see. Now this 5 minus 6 is not possible, so we will make it 5 plus 16. This will become 5. So now when we subtract this one, that will give 15, and 15 is nothing but F. Again this 5 minus 6 is not possible, so this becomes 5, and 16 adds over here. So again 16 plus 5, 21, minus 16 is minus 6 gives 15, which is F. Then 5 minus 5, 0, and 6 minus 6, 0. So yes, it is giving FF. Means this particular property is being followed over there. So that is a valid number representation in a Little Endian computer. Let us go for the next option. Little Endian is 0001 and Big Endian is 0100. Now here you can see the lower number is greater, so this is going to be in negative. So that definitely is not possible, but let's try to do it in this way. 0 1 0 0 minus 0 0 0 1. Here this becomes 0, then this becomes 16 and 1 will be given there, so 15, and then this gets 16. So this is 16 minus 1, 15, that is f. This is also f, 0 0. So this is actually giving us minus 255 because the big Endian number is bigger in case of this particular option. The little Endian is smaller, so this would be incorrect. Similarly, coming to the third option, here also we can see the big Endian number is bigger. So this may also give, if you try to check out, it will also give minus 255. So this is also eliminated. Then coming to the last one, that is 0 1 0 0 minus 0 0 1. That is the same thing which we had done over here, and it turned out to be FF, which means 255. So this one would also be correct. The little Endian minus big Endian is giving FF correctly. That is what we wanted. So for this question, the correct options would be A and D.
This is an engineering mathematics question from set theory. We are having a set S having 10 elements. So its cardinality is 10. And from this set, we need to find out the ordered tuples of the form A, B such that both of these A and B are the subsets of S. So we can say like this, A and B both. And also A is a subset of B. And here the subset they have mentioned is not a proper subset. Both can be equivalent as well. So using these three conditions, what is the number of tuples we can create out of this set S that is to be found out? So now let us consider every element one by one, and each of that element will have three choices based on these three conditions. The first one would be that let us consider that element to be X. Then first choice would be that X belongs to neither set A and X belongs nor to set B. It is in none of them. It is possible that A and B, it is both are empty. You can have empty tuple like this as well. It's allowed. So this is the first case, that chosen element X belongs neither to A and nor to B. Then second choice would be that chosen element X does not belong to set A, but it does belong to set B. By this, the third condition would be satisfied, that A is a subset of B. So it is possible for an element to not exist in set A, but still exist in the set B. And then the third choice would be that X belongs both to set A as well as set B, because both can be equivalent as well. It is possible that if all the numbers choose to be a part of both A and B, then we'll be ending up with equivalent sets. That is also allowed because we don't need a proper subset. So these are the three possible cases we will have for every element of the set S. And the set S is having 10 elements. So each of these 10 elements is having three choices to choose from. So now this would become 10 raised to 3 or 3 raised to 10. So it would be one of these that we need to identify. And how to do that? Like this. Each of these 10 elements, let us say the first element, it had three choices. It chose one from those. Then second element, it again had three choices. Third element also has three choices, and so on. So this becomes 3 to the power 10. And that is 59049. So that would be the answer for this. That is the number of tuples we can create out of the set S.
A TOC question on DFA. We have been given a language L in closure of 0 and 1. It is an arbitrary regular language accepted by minimal DFA with K states. So we need to determine that which of the given languages must necessarily be accepted by a minimal DFA also with K states. Now it is not the same DFA which is existing for this particular language L. They are just saying that there is a language L that needs a DFA with K states. So we have to determine what are the other languages from those given in the options that also require K states, and that has to be a minimal DFA. Alright, so let us have a look at the options and let us try to come up with some counter examples for them. The first one is saying L minus 0, 1, which means the language L except the string 0, 1. L is accepting, let us consider L to be a language which accepts only one string, which is 0, 1 itself. So let us create the DFA for this language L. It will accept only 0 and 1. So this is 0, 1 final state, and there will be a dead state for 1, for 0, and for both 0 and 1. So this is the DFA for the language L. Now what they are saying, L minus 0, 1, which means our L was itself accepting only 0, 1, and now we are removing that string from it as well. So now L becomes the empty language. It will read only one single state now, and hence it is not requiring the same number of states. We can also take other examples for L, and we'll come to know that whatever we take L, it's L and the language we obtain after removing this one single string from L will not always need the same number of states. So this is incorrect. Next one is L union of the string 0, 1. So for this case, we can consider language L to be, let us take some other case. Let us take L to be the empty language itself. L does not accept anything. So for that, this will be the DFA which needs just one single state. And now we are taking its union with the string 0, 1. So now this particular language will become like this, which we had considered for the first case. This is its DFA. The language which accepts only one single string, that is 0, 1. So again, L and L union of 0, 1 are not requiring the same number of states. So this option is also incorrect. Now the option C, it is saying the closure of 0, 1 minus L. So L itself was defined in this particular domain itself, and we are removing L from the closure of 0, 1. So this becomes L complement. And we know how to convert a language into its complement using the DFA. What do? We just swap the final and the non-final states. So if we consider this particular DFA itself, this is accepting the language having just one single string, which is 0, 1. If we have to take its complement, then that language will accept everything except this particular string. It will accept null string, it will accept 0, 1, 0 star, 1 star, 1 star, 0 star, everything except this one single string. So for that, what we'll be doing, we'll be swapping the final and the non-final states this way. Now as you can see, this DFA, it accepts null string, yes. It accepts 0, it accepts 1, it accepts any number of zeros like this. From here, it will go to this state, and this is having a loop on itself, so it will accept all the strings except 0, 1. It's 0, 1. See, this is 0, this is 1, and it is a non-final state. And there is no other way we can get a 1 after 0. This is the only possible path. So we cannot accept 0, 1, but after that, after 0, 1, we can have anything again. 0 plus 1 plus, not a star, it is a plus. After 0, 1, again we can accept anything, go into this state. So this is the resulting DFA, which is also requiring 4 states, and it is representing the complement language of L. So language L and its complement can be represented by the same DFA with the same number of states, only by swapping the final and the non-final states. So option C is the correct answer. Let us also look for the D. It is a concatenation of language L with itself. So here let us consider language L is a language that accepts just one single string, which is, let's say, 0. So its DFA will be represented as, it is only accepting a 0. This is the start state, this is a 0, and we'll enter dead state 1, 0, 1. So this will be the DFA for the language L that accepts only a 0. And when we concatenate L with itself, it will become 0, 0. It will have to accept a string which is 0, 0 and nothing else. So for that, this will be the resulting DFA, 0, 0 and a dead state. for 1, and for both 1 and 0. So now L took 3 states and L concatenated with L itself took 4 states. So again here we have found a counter example. So this option C, which is L complement, is the only possible solution in which L and its complement, both the languages, always require the same number of states in their minimal DFA. That is the correct answer. COA question based upon a pipeline processor. We have been given a processor having 5 stages, and those are instruction fetch, decode, execute, memory access, and the write back, which we are already aware about. Now they have given that each stage of this pipeline except for the execute stage takes exactly 1 cycle. And what about this execute state? It will take more number of cycles depending upon what is the type of the instruction being executed. We have to assume that in the decode stage we merely decode the instruction, so there is no other overhead that is being performed. The register read is performed in the EX stage, execution stage itself, so we did not consider it elsewhere separately. And this EX stage, execution stage, is taking 1 cycle for the add instruction and 2 cycles for the MUL, multiplication instruction. So these are the 2 types of instructions that will be considered for this question, and they have said that it takes 1 cycle for add and 2 cycles for MUL instruction. So now they have given a sequence of 8 instructions, which is the alternating sequence of add, MUL, add, multiply, add, multiply, add, multiply. So assuming that every MUL instruction is data independent on that instruction just before it, which means this instruction will be data independent of its previous add instruction. This particular information will be useful when we deal with the operator forwarding part. And every add instruction except the first one is data dependent on the MUL instruction, which is immediately after it. So there is dependency between them on the MUL instruction just before it. So this is not after. Both of them are dependent on their before one. Then only will dependency work out. Otherwise, it cannot be dependent on a later instruction. So both this add instruction is dependent on its previous MUL, this one on its previous MUL, and so on, except for this first one. And same thing applies for these MUL instructions as well. Even they are data dependent on their previous add instructions. So this simply means that the data, whatever would be returned by the previous instruction, would be useful for the next instruction to carry out its own processing. They are not independent of each other. The result of the previous stage would determine the result of the upcoming stage or the current stage. So that is what they mean by data dependency over here. And now, given all this information, they have defined what do they mean by a speed up ratio. That also we already know. It is the execution time without operator forwarding divided by the execution time with operator forwarding. So we will have to consider both of these cases one by one. First we'll be dealing with operator forwarding thing without operator forwarding, and then we shall calculate what is the total time required when we perform or when we make use of this operator forwarding thing. Obviously this second concept, which is with operator forwarding, that will take lesser time because we will make use of this dependency concept and the operator forwarding will be applied. So that will take lesser time, and then depending upon them we'll see what is the speed up we can achieve by using this particular concept. So we have to report that answer rounded up to 2 decimal places in this. So let us calculate both of them separately one by one. So first let us go for this operator forwarding without that. I've traced out a tabular representation for without operator forwarding, and over here these are the time units for the stages which we might require, and these are those 8 instructions sequence which we had been given for execution. So we have 5 stages in this processor, which are fetch, decode, execute, memory access, and the write back. And we have to keep in mind that this execute stage takes 1 cycle for add and it takes 2 for MUL instruction. So let us start filling out this table. The first instruction which we are having is the add instruction. So for that we will simply have fetch, decode, execute, memory access, and the write back. Simple. At t equal to 5 it is complete. And coming to the next one, which is multiply instruction, that we'll start fetching it after the previous instruction has been fetched. So it is fetched at t equal to 2. Then it can be decoded while the previous instruction is still executing. But for this instruction to start its execution, we will have to wait until this has written back. So execute for this instruction can only start at t equal to 6. And since it is an MUL instruction, it will take 2 cycles for execution. Then it's memory access and the write back. Now coming to the next one, which is add instruction again. It will be fetched here, decoded over here, but for execution it will wait until 10, then execute, memory access, write back. The next one is again MUL instruction, so it will be fetched here, decode, then execute for 2 cycles, memory access, and the write back. Coming to the next, which is an add instruction, that will be fetched at t equal to 10, then decoded at t equal to 13. For execution it will wait until 17, and then this is its execute. It will take only 1 cycle for that, followed by memory access and the write back. Then next we have the multiply instruction. For that the fetch takes place over here. Then this is the decode, execute, 2 cycles for that, memory access and the write back. Next again an add instruction, so it is fetched here, decode, execute, memory access and the write back. Then coming to the last instruction, which is again an MUL, it is fetched at t equal to 20, then decoded at 24, then it will wait for execution till here, 2 cycles for that, then memory access and finally write back. So this completes our sequence of 8 instructions that were to be executed, and we saw that the total time it took for performing this is 30 cycles, because at t equal to 30 the last write back for this last MUL instruction has been completed. So it took us 30 cycles when we used without operator forwarding thing. Now we will also check how much cycles does it take when we use operator forwarding, and then their ratio would help us to calculate what is the speed up achieved. So keeping this 30 cycles in mind, let us now proceed for the with operator forwarding thing, and we'll also perform the same thing over there also. Now moving with the with operator forwarding allowed. Here the only difference which is created from the previous one is that, for example, if the previous instruction has this fetch, decode, execute, memory access, write back, this particular sequence of cycles, then what did we previously do? We fetched the current instruction over here, decoded it when the previous was in execute state, but for executing the current instruction we waited until it finished writing back. We started executing it here. So this wasted 2 cycles. But here when the operator forwarding is allowed, and we also saw what are the dependencies existing. So in this case what we'll be doing is we will start executing the current instruction here itself after the previous one has finished its execution state. For example, if it took, let us say, 2 execute cycles, then what we'll do is we will fetch it after in the immediate next cycle after it was fetched, then decode it in the same way. But here we cannot execute it because the previous is still in the execute state itself. So we'll wait in this cycle and execute it here. Then memory access followed by the write back. So this will save us a few cycles. So let us fill the table in the same way for this one, and let us see how much cycles is it taking. So for the same set of instructions, the first one, which is an add instruction, we will be having fetch, decode, execute, memory access, write back. Then the next one, which is MUL instruction, fetch it here, decode, it will take 2 cycles for execution, memory access, write back. Then for this add instruction, fetch it here, decode, but it cannot execute here because the previous one is still in the same stage. So wait in this and execute it here. Then memory access, write back. Next, which is MUL instruction, fetch it here, decode, execute, it will take 2 for that, memory access, write back. Next is add instruction, fetch it here, decode, cannot execute here, so execute it here, then memory access, write back. Next is MUL, fetch, decode, execute for 2 cycles, memory access, write back. Next is an add instruction, so fetch it here, decode, wait here, execute, memory access, write back. Then coming to the last instruction, which is again an MUL, we will be fetching it here, decode, execute for 2 cycles, then memory access and the write back. So this completes our execution. And how many cycles did it take this time? It took just 16 cycles because we were able to write back the last cycle for this instruction, MUL instruction, in the 16th cycle itself. So with operator forwarding, it took only 16 cycles. And without operator forwarding, as we previously saw, how many cycles did it take then? It took 30 cycles. So the speed up was defined as the ratio of number of cycles it was taking without operator forwarding divided by the number of cycles it was taking with operator forwarding. So we will be dividing this 30 by 16 and that will be our answer. So it gives us 1.82 or something, whatever it is giving. We have to round it off to 2 decimal places, and that would be the speed up ratio we can achieve given this 5-stage pipeline processor. So this is how this problem will be solved. This is a numeric type question from TOC. We have been given a DFA and we need to determine the number of strings of length 8 that are accepted by the given DFA. So in this DFA you can see that there is only one final state and this is the start state. So how many ways are there to reach from the start state to final state? The first way would be we traverse this way. First will be 0, then 0, and then we go this way to the final state. Now what string did we generate from this path? 0, 0, and for the third place we have both the choices, 0 as well as 1. So we can keep it blank, indicating that it has both the possibilities. So these 3 steps are done. Now the next 5 states are to be done through this loop itself in the final state. So, and even in those 5 states we have 2 choices each. We can take either 0 or 1. So the next 5 steps, 1, 2, 3, 4 and 5, all of these 5 and plus this one, so all of these 6 states are ambiguous. We can take either 0 or 1 at all of these places. So if we follow this path, how many strings can we generate? 2 to the power 6, because we are having 6 places where we can substitute either 0 or 1. There are 2 choices each. So 2 raised to 6 is 64 strings we can generate through this path. Now let us say we follow this lower path, 1, 1 and this one. Again at this we can say that 0 and 1 both are possible. So the strings will be beginning with 1, 1. The third place will be ambiguous. It can have either 0 or 1. And the next 5 are to be completed in this loop itself. So again those 5 are also ambiguous. So the number of strings we will be generating from this path will also be 2 to the power 6, which is 64. Now is there any other path we can use to reach the final state? We can go like this way, 0, then come down like this, 1, and then from here we have no other choice, we will need to go like this. So what string did we generate? 0, 1. For the third position again we have 2 choices, and the next 5 will always be completed in the final state. So 1, 2, 3, 4 and 5. Again this path gives us 2 to the power 6 equal to 64 strings. Now the last path we can observe in this DFA is this one. We take 1 first, then go here with a 0 and then like this. So from this path we are generating the strings beginning with 1, 0. Again the next 6 places will be ambiguous. They can occupy either 0 or 1. So that will also give us 2 to the power 6 equal to 64 strings. And there is no other path available in this DFA, so that this is all the possible strings we can generate beginning with 0, 0, 0, 1, 1, 0 and 1, 1. And next 6 places are all ambiguous. We can place either 0 or 1. So the total number of strings we got is sum of all this, or you can say 4 times of 64, which is 256. So this will be our answer, 256. And there is one another way in which you can derive this answer. You can say that if we name the states like this, let us erase this out. Let us number the states as, it is called this Q0, Q1, Q2, Q3, Q4 and Q5. As you can see, from Q2 to Q5 and Q4 to Q5, the path is same. It is giving us either 0 or 1, both are allowed. So we can actually merge these two states together. And in the same way, this Q1 and Q3 can be merged together. So this is not a minimal DFA. We can minimize it further and it will result into something like, let us draw it here. Okay, this DFA can be converted into like this. This is our Q0. We have merged Q1 and Q3 together. Let us call it capital Q1, capital Q2. So this can be our resulting DFA. From Q0 to Q1, we will have both of these, 0 as well as 1. From this capital Q1 to capital Q2, we'll again have 0 to 1. This will again be 0 to 1. And here we are looping. So as you can see, this DFA is actually the DFA with all the strings with length at least 3. As you can see, length 1, 2, 3. It will accept all the binary strings with length at least 3. And from this, can we determine the number of strings with length 8? Yes, we can. For the first 3 steps, we will take 2 to the power 3 because each of them has 0 and 1 both. And then for the next 5 states, which are to be completed through this loop, for that we'll be using 2 to the power 5. So in effect, it becomes 2 raised to 8 or 256. So this way also we can do and get the same result. So there are 256 8-length strings accepted by this DFA. And what is this DFA? It is accepting all binary strings with length at least 3. So our answer is 256. This is a digital logic question based upon K-maps. We have been given a Boolean function with 4 variables w, x, y and z such that these 4 expressions hold true. And we need to determine the number of literals in the minimum SOP form for the expression f. So we can start with making a 4x4 K-map with these 4 variables w, x, y and z. It will look like this. On the row side we can take wx and here we can take y and z. Then the terms will be represented using 0, 0, 0, 1 and 1, 1, 0. And similarly here. Now the first expression is saying us f of w 0, 0, z is 1, which means the values corresponding to x and y are set as 0. So if we set x and y and keep w and z independent, they can take either 0 or 1. Then irrespective of their value, the result is always 1. So the terms corresponding to that in our K-map will be, let us say for x we are setting 0. So these two are the favoring columns. Similarly for y equal to 0, these are the 2 rows which will be holding true. So now irrespective of the values of w and z, these 4 will always have the value as 1. So we can set them to be 1. Now going to the next one, it is saying f of 1x 1z, which means w and y are fixed as 1 while x and z are independent to take any value. So which are the rows and columns corresponding to this expression? This particular w equal to 1 corresponds to the last two columns, while y equal to 1 corresponds to these last two rows. And what is their intersection? It is these four cells. And what is the value we'll be putting in these four cells? It is not either 0 or 1, it is dependent on the value of x and z. And how is it dependent? It is x plus z. So if we look at this particular cell, in this cell the value of x is 1 while for z is also 1. Hence x plus z will give us 1. Now coming to this next cell, here the value of x is 0 while z is 1. So their OR will again give us 1. Coming to this cell, value of x is 1 while z is 0. So their OR will again be 1. But for the last cell, x and z are both 0. So their OR operation will also give us 0. So this is how the second expression will be utilized. And now moving to the third one. It is saying f of w1 yz, which means only x is the independent variable. X is set as 1 while w, y and z are all free to take any values from 0 or 1. So which are the cells corresponding to x equal to 1? This is value of x as 1. So all of these 8 cells will satisfy that criteria. So what's the value we'll be putting in these cells? It is dependent on the other 3, which is w, z and y. So how do we, let us say for this particular cell, it will be replaced with the value of w, z plus y. Now for this cell, what is the value of w? It is 0. And the value of z is also 0. But value of y, it is 0 as well. So 0 plus 0 will again give us 0. Now coming to this cell, the value of w is 1. You can simply look at these indices. W is 1, z is 0. So their AND operation is 0. And then and ORing to it the value of y, which is also 0. So this cell will take the value 0. Coming to this cell, here we have w as 0, z as 1. So the AND will be 0 and plus y, it will again be 0. Now coming to this one, w is 1, z is 1. But y is 0. So this becomes 1 plus 0, giving us 1. Coming to this one, here w is 0 and z is 1, but y is also 1. So for this last 4 cells, since the value of y is 1, so whatever is the value of wz, ORing it with 1, wz plus 1 will always be 1. So these last 4 cells will take the value 1, and we already had 1 in these two, so that does not change. So now using these 3 expressions, we have filled the values in all these cells except these 2 which are left out. So they will be kept as we can say that they are the ambiguous values, or we can say sigma over there, so that the resulting expression for f of wx, yz, that will be determined using the K-map which we have just formed, and we can now form groups in it like this. These are the minterms having 4 terms. This is another 4. This is another one. Using these don't care terms, there is no use of including them anywhere, because we cannot anyway form an size 8 minterm. So we have only got 3 minterms having size 4 each. Now looking at this particular minterm, what is the expression it is giving out? The common term is this one. So it is x bar, and from the row, this is the common thing, which is y bar. Plus, now looking at this minterm of size 4, the common column is the first one, which is w, and from the row we get the second one, which is z. So wz, and the last minterm, which is here at the bottom, again of size 4. From column it is giving out x, while from row it is giving y, because that is the common term. So this is the SOP expression we have got for the function f, and they're asking us for the number of literals in this expression. So we can see that there are 1, 2, 3, 4, 5 and 6 literals in this SOP expression. So the answer for this question will be 6. Operating systems question from process synchronization. We have been given a computer system which is having multiple shared resource types, and there is only one instance per resource type, which means we have different types of resources R1, R2, R3, but there is only one instance of every resource available, and every instance can be owned by exactly one process at a time. So there is no sharing of instances. Owning and freeing of resources is done by holding a global lock. So we already know about the shared locks, exclusive locks, all those which exist over here. And then we have the semaphore things which helps for process synchronization. The following scheme has been given over here in the form of this function, which is the synchronization mechanism being used. So that is customary built mechanism they are using. Let us have a look at what it is doing. There is a function own resource, and this is a resource instance R which is passed to it. So what it is saying that if any process wants to acquire a resource, then this is the protocol that it needs to follow. Let us see what is it. First, it will have to acquire a global lock L. So this global lock is similar to that exclusive lock which we are aware of. So first of all, it will acquire a global lock, and then it will check if the resource instance R is available or not. If it is available, then acquire it, use it, and release the lock. So that is how, if the resource is available, then the process can readily use it. But if it is not available, then in the else case, when the resource is not available, which it is requiring, then what should it do? If that resource is owned by another process P, now there is only one instance of every resource, and if it is not available for the current process, it means that it would definitely be owned by some other process. So let us say the instance which the current process is requiring, that R, it is currently owned by some other process P. Then what will this current process do? It will terminate P, which means it will kill that process which is holding the resource that it wants. So if I want something from you, then I will kill you and then I will acquire that from you. So that is the thing going on over here. So it will terminate that process P. It will release all the resources which were being held by that process P, and after that, when all those resources are freed up, then it is free to acquire that R. So it will do so. It will terminate that process, kill that process, then acquire the required resources, use them, and after that it will also restart the process which it had killed. So now this process P will again need to start from the beginning. It will also once again need to acquire all the resources that it needs. So it will proceed on its own. But for the current process which is executing this particular function, what will it do? It is simply terminating it, acquiring its resources. It is restarting that killed process and then releasing its own lock. So this is the mechanism being used. So as we can see, there are some problems in this mechanism, that in this the processes have no priorities. Any process can kill any other process and acquire the resources. So let us check out what are the possible outcomes for this. But before that, let us also understand the difference between deadlock and a live lock. Then only we'll be able to analyze which of them is existing in this scenario. As we know, in deadlock, what happens is there is a loop kind of thing. There are 4 necessary and essential conditions that we are aware of, that there is circular weight and all those things. Mutual exclusion has to be there. But what primarily leads to this deadlock is that the processes wait for each other in an infinite loop. There is no moving ahead. All are stuck. No one can exit out of that loop. There is no progress. So that is what we call as a deadlock. But live lock is a little bit different from that. Starvation exists in both of them. But the difference between deadlock and live lock is that in live lock you can take an analogy of, it's like a traffic jam that you are continuously checking if the situation has resolved or not, and the processes are still waiting. There is no progress, but it is not like an infinite loop. They are not dependent on each other like this, which was existing there in the deadlock. There is still no progress in this. There is starvation, but it is like you are continuously banging on the door. You are checking if the resource is free, and as soon as it gets free, you are going to acquire that. So it is not like the processes are dependent on each other. They are just simply waiting for their turn. They are continuously checking if their required resource is free or not, and there is some movement. Here there was no movement at all, absolutely no movement, but here we have some movement, but there is no progress. There is starvation. So we can say that there is no useful work being done over here. Some work is being done, there is some movement, but that work is not useful. So that is what we call as a live lock. So now coming to this given scenario, which of these will exist? Now first of all, check if there is mutual exclusion there or not. As we just saw, at a time only one process can acquire a resource instance, and if the instance which I need, if it is free, then I will acquire it. I will not share it with anyone else. But if it is not free, then I will kill the process that is currently holding it, and I will snatch it from that. So at a time, only one process is executing, only one process is acquiring a resource. Hence, there is mutual exclusion, and there is no violence of mutual exclusion in the synchronization mechanism. So this states that our option D is incorrect. There is no violation of mutual exclusion property in this scheme. So now if there is mutual exclusion, then there can be a deadlock. But do we have a deadlock over here? Let us see. Is it possible over here that all the processes will wait for each other in an infinite loop? No, it is not possible, because every process can kill every other process. So I'm not bound to wait for someone. I will simply go and kill that process, and I will acquire the resource which I need. But it is possible that in the meantime, I might get killed by someone else. So let us take an example. There are three processes, A, B, and C. A needs a resource that has been acquired by B. So what will A do? A will go and kill B, and then A will start executing. But at the same time, what does C do? C also wants a resource that is being currently held by A. So C will go and kill A, and it will start to execute. But here, as we saw, it is the terminated process also gets restarted. So these A and B will be restarted. So now they are free to go and kill C and acquire the resource back from them. So this will keep on happening. They will keep on killing each other and acquiring resources. So there is some useless work being done over here. So this is what we will call as a live lock instead of a deadlock, because they are not infinitely stuck. They are free to kill each other and try to execute, which they will possibly not be able to do. So in this scenario, there is a live lock, not a deadlock. So this scheme ensures that deadlock will not occur. And we also know one more thing, that deadlock and live lock, they are mutually exclusive, which means both of them cannot exist at the same time. You will have either a deadlock or a live lock or none. It is not possible to have both of them simultaneously. Hence, if we are having live lock here, deadlock cannot be there. So the scheme is deadlock free. Then the third option, the scheme may lead to starvation. Yes, starvation is there in both deadlock as well as a live lock. Why does starvation occur in live lock as well? Because work is being done, but it is not useful. So processes are starving for the resources. Hence, there is starvation as well. So we got A, B, and C, all three as the correct options. This was an MSQ type question, so we'll be reporting all three. Engineering mathematics question. We have this matrix P, which is a 4 cross 5 matrix, which means it will be having 4 rows and 5 columns. So we can say that P constitutes of 5 column vectors. Let us call them C1, C2, C3, C4 and C5. These are all the column vectors and there will be 5 of them because it is a 4 cross 5 matrix. So this is how we can represent the given matrix P. And now what they have given, Px equal to 0. Now we wrote P as a matrix consisting of 5 column vectors, and this X is another matrix such that their product is giving us 0, and the solution for this equation that becomes a scalar multiple of this given matrix. So what we can say that the given matrix is actually like this: 2, 5, 4, 3, 1. Those are the separate elements in it, and that's transpose given over there. So this is our P and its transpose. So this is a row matrix, so its transpose will become a column vector kind of thing. So when we take the product of them, that has to be scalar multiple. So what we'll say that this matrix X, that can be written as 2k, 5k, 4k, 3k and 1k, and then transpose of that. This is because what did we do? We took this given vector as a reference and then we multiplied some constant k with it to get the given matrix X as this way. Then it's transpose. Now what we will simply do is, we have this P, we have X, we will simply multiply them and see what do we get. So now this is its transpose will be taken. So what will happen is, when we try to multiply them, their corresponding elements will get multiplied. So the result of Px that we will get, it will be 2k times C1 plus 5k C2 plus 4k C3, 3k C4 and 1k, or simply k times of C5. But we wanted the solution of Px equal to 0, so we will say this equal to 0. Now from all of this we can again take back that common factor k outside, which we had ourselves included in it. So after removing that k, we will get an equation that will be 2c1 plus 5c2 plus 4c3 plus 3c4 plus c5 equal to 0. Now from this we can see that all of these 4 are having some coefficients with them. This one is alone. So what we can do is, we can write this C5 in terms of the other 4. We can say C5 equal to minus 2C1 minus 5C2 minus 4C3 and minus 3C4. So what did we just do? We wrote one column vector as a sum of other 4, not actually as a sum, as some combination of the other 4 column vectors. So we can say that this C5, it is a linearly dependent column vector because the value of C5 is dependent on the value of C1, C2, C3 and C4. So this C5 becomes linearly dependent column vector, and these 4 from C1 till C4, they become linearly independent column vectors because they are not dependent on each other, but all of them put together they determine the value of this C5. So what are we actually having? We have 4 linearly independent column vectors and 1 linearly dependent column vector. So in this 4 cross 5 matrix, how do we actually determine the rank of a matrix? Rank is nothing but this interpretation as the number of linearly independent column vectors in it. Or when you represent it this way, then what do? We count the number of zeros and ones. We count the rows in which how many zeros are there. Previously we have ones, then here we take zeros. So that actually translates the same interpretation that we are essentially counting the number of linearly independent column vectors, and in this case we have got 4 such column vectors. So we can say that the rank of this P is same as the number of linearly independent column vectors in it which is 4. So the answer for this question will also be 4. This is a probability question. We have an examination in which a student can choose in which order the two questions, which are question A and question B, have to be attempted. Both of them are compulsorily to be attempted. So there will be two different strategies of doing so. Either do A first and then B, or do B first and then followed by A. But there are three constraints to be kept in mind. It is saying that if the first question is answered wrong, then the student gets 0 marks, which means for both of these two orders, the first question, whether it is A or it is B, if that first question is answered incorrectly, then irrespective of the second question, the student will be awarded 0 marks itself. The next one is saying that if the first is answered correctly, second is not answered correctly, then marks will be given only for the first question. That makes sense. If first is correct, second is not correct, marks will be given for the first one. Then if both are correctly answered, then the total marks will be given for both the questions. Fine. So now they have given the probabilities of answering both the questions A and B correctly and the marks for both these questions. They have been given in this table. So what we want to do is, assuming that the student always wants to maximize her expected marks in the examination. So in order to maximize the marks, we have to determine which of these two orders will be good to go with. Either do A first and then B, or do it in the order BA, so that the total expected marks can be maximized. So for both of these two cases, we will be finding out what is the expected marks, and then whichever gives us the higher expected marks, we will be going with that order. So first, let us go with the order AB. So question A has to be answered first and then followed by B. So in this case, the expected marks will be given as, let us assume first that this first question A, it is answered incorrectly. And what is the probability of that happening? It will be 1 minus 0.8, so 0.2, and for this one, for question B, it will be 0.5 itself. So coming here, probability of answering the first question incorrectly, how much is it? 0.2. And in that case, how many marks will be given? Straight away 0, without looking at the second question. That is the first constraint we were given. So now next, another case is that first question is answered correctly, and that is having a probability of 0.8. Then, so now first question is done. Coming to the second one. Now assume that the second is answered wrong, and it is having probability of 0.5. So here first is correct, second is wrong, so marks will be given only for the first question, so 10 marks will be given. Then coming to the third case, that both the questions are answered correctly. So first is answered correctly, second is also answered correctly, 0.5 probability is there. So in this case, how many marks will be given for both the questions, which means 10 plus 20 equal to 30 marks will be given for this case. So what is the expected marks we get? This is 0. This becomes 0.8 into 0.5, 10 plus 30. So that is 8 5 is 40. So 0.4 times of 40, that gives us 16. So if we follow the order AB, then we get 16 as our expected marks. Now let us see if we follow the order BA, then what is the expected marks that we can get. Let us do that over here only. Now for this case, B is our first question and A is the second question. So for that, let us calculate the expected marks. Here B is the first question. Let us say first question went wrong. And what is the probability of that happening? It is 0.5. So now if the first question itself is wrong, then total marks given will be simply 0 plus. Now the first is answered correctly. 0.5 probability is there. Now second question, which means question A, that is answered wrong. What is the probability of it? 0.2. So in this scenario, how many marks will be given? Only for the first question, which means for B. So 20 marks will be given. Plus of both are answered correctly. 0.5 into 0.8 into, if both are correct, then 30 marks will be given. So here what is the expectation? We get this is 0. So this becomes 0.5 times of 0.2 into 20. How much is it? 4. Plus of 0.8 into 30. So this gives us 24. So that is 28 by 5, 28 by 2, and that gives us, this is 14 marks. So if you follow the order BA, then the expected marks is 14. But it was given that we want to maximize the total score, so we will be going with this first order, which is AB, and in that case the expected marks will be 16. So from the given options we see that option D is matching. First do question A, then do question B, and the expected marks will be 16. So this is the correct option. This is a DBMS question based upon SQL query. A relational scheme has been given below that is used to store the information about employees of a particular company. In that, the employee ID is the key and department ID indicates the department to which those employees are assigned to. So now this is the relational schema that has been given. There is an employee table in which there is employee ID, which is the key for that table. Along with that, there is name, gender, salary, and the department ID for the corresponding employees. So now they have given an SQL query, which is select department ID count star from employee, means this table itself, where gender is female and salary is greater than, select average salary from employee, and then it is grouped by department ID. So we have to determine what actually this query is doing. So let us check out that first. Select the department ID and the count star. So basically what we are wanting, there has to be department ID and the count star for that particular department. It is being grouped by department ID. So let us say we have departments A, B, C, so on, and for each of them some count will be returned. So this will be the format of the tuples returned by this query. And from this employee table, where what is the condition given? Gender equal to female, which means for every female, what are we doing? We are selecting those females actually whose salary is greater than, select average salary from employee. Now this is an independent subquery. It will be evaluated separately. Select average salary from employee. So here we don't have any condition that whether the gender has to be male or female or to which department that employee has to be belonging. So nothing is given. It is a simple straight query. Select average salary from employee. So it will return the average salary of all the employees in that organization. So let us say this will return some number. Let us say 20,000. So now what we are doing? We are selecting those employees who are females and their salary is greater than this number. And then for such employees, what we are doing? We are taking their count. So what does this query do? It is giving us department wise the count of female employees in every department whose salary is greater than the average salary of the entire company. So let us say in department A there are 2 female employees whose salary is greater than 20,000. Similarly, department B, there are 5 such employees, women employees. In department C, there are none, or let us say 2 or 0, whatever. So grouped by department, it means for every department, it returns us the number of female employees having their salary greater than the average salary of the entire company. So that is what this query is doing. Now, above query gives for each department in the company the number of female employees whose salary is greater than the average salary of. So we just determine what this query is doing. It gives us the number of female employees in every department whose salary is greater than the average salary of the entire company. So we'll be going with this option, employees in the company. That has to be correct because there is no condition on this subquery about department or about gender or anything. So it is simply returning this one. So option B will be true for this. This is a computer networks question based upon error detection using CRC. We have been given the CRC generator polynomial as x cube plus x plus 1. So that will convert into the CRC generator as first we can convert it into the polynomial form entirely because the x squared term is missing. So that will become x cube plus 0x squared plus x plus 1. And then taking out its coefficients, we get the CRC generator as 1011. Now the message bits, it is a 5-bit message from M0 to M4, which is given as 11000. That is to be transmitted using CRC as error detection mechanism. The check bits will be 3 because our generator has 4 bits. So we will be appending 3 check bits to it and then transmitting it over the link. The check bits to be appended in this message originally will be 000, and then we shall be performing the CRC mechanism on that to generate the actual check bits C2, C1 and C0. They are to be determined that what exactly has to be appended at the end of this message before transmitting it, so that on the receiver side it can once again perform the same mechanism and check if it is getting 0 as the result. If not, then it will detect that there is an error in the transmitted message. So we shall start with the given message, that is 11000, and appending 3 zeros at the end of it. After that, we perform this XOR operation using the generator which we have got, that is 1011, and XORing gives us this 1 and 1 will give us 0. So this is 111 followed by 4 zeros, and we will once again perform the same procedure with 1011 until we are left with 3 bits at the end. That will be our generator bits. So again this 11 gives 0, so it is 101000. When we do it one more time, it gives, now this 11 is 0 0 0, and at the last we are getting 100. So now we have got these 3 bits which are the actual CRC bits that has to be appended at the end of this message. This is our original message, and to its end we will be appending these 3 bits and then transmitting it over the link. So the check bit sequence which we have been asked, C2, C1, C0, is actually 100 for this case. So the correct answer will be B. This is a numerical type question from compiler design. We have been given an augmented grammar, and the set of terminal symbols present in that grammar is represented using this set. The state I0 is defined as closure of S0 derives dot S. So basically we are talking about its LR0 items. The number of items in the set go to of the state I0, here it will be a comma, on this terminal symbol, and then what will be the resulting set out of that will once again be taking the transition on the same terminal symbol. Then the resulting go to set that will be obtaining, for that set we have to return the number of items present in it. Now as we can see, there is no look ahead present, so this is definitely LR0 grammar. The state I0 is given to us. Let us count the number of items in this. It is 1 2 3 4 5 6 7 and 8. This is our state I0. From this we will be taking the transition first. This inner one will be evaluated, and then whatever will be the result, for that we'll be doing the same procedure once again. So let us see what is the result we are getting for this I0 itself. We'll be noting down all those transitions here. S dash derives S derives S hash CS, S derives double S derives S at the rate, S derives the symbol S closing one, and then S derives A, S derives B, S derives C. So we have got the item set I0. Now here we can see the terminal symbol for which we had to take the transition, that is present over here. So we'll be taking that transition for this symbol, and let us say the resulting state is I1. So now when we take that particular move for this particular production, then what will it result into? We'll be moving one step ahead of this. So it will result into something like that less than symbol dot S. S derives the terminal symbol dot S and the closing symbol. That is what it will result into. And there is no other the same terminal symbol present anywhere else other than this production. So now we are actually done, but as you can see here we have encountered a dot S. So what does that imply? That we will be needing to include all the productions for S once again in this state itself. So we'll be doing that. S derives, we'll be just copying all the productions of S from state I0 itself to I1. So that will give us, starting from here, S derives dot S hash CS, S derives dot SS, S derives dot S at the rate. This we have already done with. So now previously what we did was, it was a move which we took on this terminal symbol, but now since we are including the productions starting with S, this will again be included, but dot will be present at the beginning. So it will result into S derives dot terminal symbol S closing, and then same S derives dot A, S derives dot B, S derives dot C. So with this we are actually done with this inner part, the transition of I0 on this symbol, and the resulting state we have got as I1. So now we will be evaluating this one. The go-to of state I1, it is actually like this, go-to of state I1 for this symbol. Now that is what we have to evaluate. So now we can see in the state I1 that required symbol is present over here. So when we take the transition for that, we'll be getting a production something like S derives opening bracket, let us call it, or less than symbol, whatever, dot S closing. So have we seen the symbol somewhere? This production rule, it is present as it is over here. And then since we have also encountered a dot S, we'll be once again including all the productions for S. So actually what is happening in effect is, we will be reaching to the same state on taking that transition, because this particular production for the less than symbol, it will be giving this one, and then since there will be dot S, we'll be once again including all the productions of S. So this is the same state I1 which will be looping into by taking the outer production. So the resulting item set is I1 itself. So we'll simply be returning the number of items present in this set I1. So let us count 1, 2, 3, 4, 5, 6, 7 and 8. So simply 8 is our answer. This is a COA question from caching. They are telling about a two-level inclusive cache hierarchy L1 and L2, where L2 is the larger of the two, which means we have a cache hierarchy L1 and L2 such that L2 lies above L1. It is a larger one. So we have to consider these two statements and determine which of them is true. First one is saying that read misses in a write through L1 cache. So this L1 is a write through cache. It does not result in write back of dirty lines to the L2. So first let us understand all these terminologies. What is write through and what is write back? These are the two types of cache we have. in case of this write through cache, what happens is that the data is simultaneously copied to all the levels, which means in L1 and L2 we will be simultaneously updating the data. While in case of this write back cache, what happens is that the data is updated. Let us say here we have memory and here we have a cache. So in case of write back, the data is updated in cache only for the time being, while it is updated in memory at a later stage, not simultaneously. In case of write through, both are updated at the same time, but in case of write back, that does not take place. Let us also understand the statement S2 first, then we will discuss which of them is true. Now this one is saying a write allocate policy must be used in conjunction with write through cache, and no write allocate policy should be used with write back cache. So now we got to know what is a write through cache and a write back cache, but let us also understand these terminologies: the write allocate policy and the no write allocate policy. Now these are the two policies we usually use in the cache while writing. Let us understand each of them. In this write allocate or the write allocation policy, what we do is, this is memory, here we have a cache. So in this, the data gets loaded from this memory into the cache and then it is updated, which means before updating we first bring the copy of that data from memory to this cache and then it gets updated over here. So that is about write allocate. We don't update the data directly, first we load it into the cache. While in case of this no write allocate policy, what happens is, again we have this memory and this cache. So in this no write allocation policy, we directly write the data, which means data is directly written in this main memory without involving the cache. So no copy of this data is loaded into the cache, it is directly updated in the main memory. So that was about the write allocation and no write allocation policies. And these are the two types of cache we have, and there is a certain mapping we can have, such as these are the types of cache: write through, write back, and these are the allocation policies. We can either have write allocation or no write allocation. Now the thing is, both of these policies can be used with any of these cache. It is possible that with a write through cache we can have a write allocation policy or a no write allocation policy, and in the same way with this write back cache also we can use both of these policies. But which is the optimal mapping? That is what they are asking us in the statement S2. So first of all, coming to statement S1, what it is saying, that it is talking about the read misses. We already know what is a read miss and what are the dirty bits. That is the operating system's concept. So here what will happen is, this L1, it has been given that it is a write through cache. So if there is any read miss in this write through cache, then that will result in a read allocate policy. Here we were talking about the write policies, whether we should do write allocation or no write allocation, but here if we are having a read miss, then that will cause a read allocate. There will be no write back in this case. Because it is a write through cache, then both these L1 and L2, because L2 lies above in the hierarchy than L1, so both of them will be updated in the same write operation, because that is what we saw over here. Write through cache, it deals with simultaneous updates. So both L1 and L2 will be updated during the same write operation. So this will not result in any dirty bits, and hence there will be, because it is a write back cache, there will be no dirty blocks and no dirty bits. Hence in case of a read miss, it will simply bring this missed block from L2 to L1. What do we mean by a read miss? That we were searching for a block in the cache which was not present there. So in case of this write through cache, what will happen is that missing block in L1 will be fetched from L2, And after fetching it, what we'll be doing is we will replace, let us say L1 has these two blocks. It wants block number 3, it is having block 1 and block 2. So it will fetch this block 3 from L2 and it will replace one of these blocks using it. But there will be no need to write the copy of this block 1 back into this L2 because it will already be there. It will already be there in the updated format itself. So we can directly fetch it and there is no need to write back. So this tells us that the statement S1 is true. And now coming to S2, here they are talking about the mapping between the type of cache and the policies to be used with them. So let us understand this using this example. Let us say if we generally, what happens is the write allocation policy that is generally not used with the write through cache. What will happen if we use this particular pairing? Let us see. Because it will become then unnecessary to bring the data from memory to the cache. We brought the data from memory to the cache and then it will be updated in both the cache as well as the main memory because it is a write through cache. So that requires us multiple updates and it is unnecessary. That is an overhead. So we usually avoid this particular mapping of write allocation policy with write through cache. This is not used. And then in the same way, what would happen if we use this no write allocation policy with a write back cache? Then in this case, what will happen is this is memory, this is cache. So here what will happen, the data updation in memory will take place 2 times because first time because of the write back policy and second time because of this no write allocation policy. So it will involve us to have two times of updates. So again this particular pairing is not used. So this no allocation policy with write back cache is also not used. But in theory all the 4 mappings are true, but in practical usage we go for write through cache and no write allocation policy, write back cache and write allocation policy. So what are they saying? Write allocation must be used with write through cache. Is that true? Write allocate with write through cache, and they're saying must be used. So this becomes incorrect. So as a result, statement 1 is true and statement 2 is false. So we will be going with option A. This is an operating systems question based upon process synchronization and multi-threading. We have this multi-threaded code segment given to us in a mix of C and pseudocode, which means in the C-like language, the piece of code has been given that signifies the synchronization mechanism that is being used for these threads. There are 2 processes that are invoking it, P1 and P2, and each of these processes spawns 2 threads, T1 and T2, which means process P1 as well as process P2 each creates 2 threads, T1 and T2. So now what they are saying, which of these statements is or are true regarding the value being printed by this program. So let us have a look at this code. It is declaring a global variable x initialized to 0, and then there is a lock L1 that will be used as the synchronization mechanism. Then there is this main function in which the process is creating its first thread T1, and that T1 will go and execute this function foo. In the next line, this thread T2 is being created, which will again execute this program function foo over here. And the same thing is done for both the processes P1 and P2. Then we wait for the 2 threads to finish their execution, and then finally we print the value of x. So now let us have a look at what happens in this function foo. It is initializing a local variable y as 0, and the global variable x is already 0 for the first time. Then the thread acquires a lock L1. So this lock here will ensure that there is mutual exclusion between them. So at a time only one thread will be executing this program. And what it is doing, incrementing the value of x by 1. So now x becomes 1. Also y becomes 1. After both these operations are performed, it releases the lock and prints the value of y. So for the first time, what is the value of y that will be printed? It is 1. But because this y was a local variable, what happens when this same function is called again for the second time by another thread? The same lines of code will run again. Y will be reinitialized to 0, but x being a global variable, it will stay at 1 only. It will not be changed back to 0. So now what happens? Y has become 0. This is the second iteration for the same function we are doing. The next thread which is executing it, it acquires this lock, performs both the increment operations. So x will now be incremented to 2, and y being local, it will be incremented to 1. So then it releases the lock and prints the value of y. So y will again be printed as 1 only because it is local to this function. So as many times as we execute this function, the same value y equal to 1 will be printed in every iteration. But for x, it is global, so it is not reinitialized between the consecutive function calls. So by the end, what has happened is y has been printed as 1 both the times and x has become 2. So here we return after performing the function call at foo. Here again we return after both these function calls, x has become 2, but it has not been printed yet because printing occurs afterwards. Wait for the two threads to finish execution. Both the threads will be simultaneously executing this piece of code, but after one execution, x would have become 1, but we will not be printing it. We will be waiting for the two threads to finish their execution. Means we will wait to achieve the final value of x. After one iteration, it has become 1, and after the next iteration, it has become 2, and then when both have completed their execution, finally we print that value of x. So here what will be printed will be 2, because this print statement is executed after both the threads have finished their execution. So what do we print? Y is printed as 1 2 times by each of the threads, and when both are done, then x is printed only once and the value printed is 2. So this is what we get as the output from this piece of code. Let us have a look at the options. First is saying that both P1 and P2 will print the value of x as 2. So this we saw for one of the processes, because process P1, it had two threads, T1 and T2, which performed this particular thing. First, we assume that T1 executed and it made x equal to 1. Then T2 executed the same function and it made x equal to 2. So that is what has happened for one of the processes. And here, both the processes are doing the same thing. Same piece of code is being executed. So both will print value of x as 2. So this is correct. Then at least one of P1 and P2 will execute the value of x as 4. X will not become 4 as we saw. For both the processes, we'll begin with x equal to 0 and its two threads will make it 1 and 2. So the final value of x printed is 2 itself, not 4. Then option C is saying that at least one of the threads will print the value of y as 2. Y never becomes 2 because it is a local variable. So every thread will print its value as 1 itself. Both T1 and T2 in both the processes will print the value of y as 1. So this is the output for P1, and in the same way for P2 will also get the same output 1 1 2. All of them are printing the value of y as 1 only. So this is also correct. So we got options A and D both to be correct in this. This is a mathematical logic question. We have been given a propositional equation given by S, and for that we need to determine which of the given options is or are correct. It is an MSQ type of question. Now the first three are talking about whether S is a tautology or contradiction, but last one is talking about its antecedent and its consequent part. So if we solve this option D, then we will be able to determine which of these three is correct as well. So first let us look at the antecedent part. What is antecedent? It is the left part of the given logical equation. So for the given equation, the antecedent will be P and Q implies R. That's the antecedent, and consequent is the right part, which is beyond the implication sign. So the consequent here will be P and Q implies R. So let us try to simplify these two and check if they are logically equivalent or not. For the antecedent part, we have P and Q. You can call it, let's say, T. So it is like T implies R, and we know that if we have anything like A implication of B, then we can decompose it as negation of the left part or right part. So this can be written in this using De Morgan's law, and hence the given equation antecedent part can be written as negation of P and Q, and this implication turns into OR, and we have R over here. In the next step, we can further take this negation symbol inside, and then that becomes negation of P or Q or R. Now let us also check the consequent part, and we shall then compare if both are logically equivalent. So here again we have an implication. So we have two choices. Either we can simplify this implication first or this inner one first. If we go for this inner first, then we get P and Q implies, this implication we break down into negation of Q or R. Now we break down the second implication, that becomes negation of P and Q or negation of Q or R. This negation, when we take it inside, that becomes negation of P and converts into OR. So OR, then we have Q. This negation symbol will go to both P and Q, so it will be negation of P or negation of Q. And in the same way here as well, in the antecedent part also, this negation will go to both P and Q, so this will become negation of P or negation of Q. That is the correct simplification. And here next we will be having this OR, same as it is, negation of Q or R. Then last step, it becomes negation of P or negation of Q or negation of R. It was just 2 times and we wrote that 1 time itself. So now we can see that the antecedent as well as consequent part have been brought down to the same equation, and hence we can say that both of them are logically equivalent. So the given option D is true. Now since we got the left part implies right part, this is holding true. The antecedent is implying the consequent, which means that whatever we have in the antecedent part and whatever we have in the consequent part, the given implication will always hold true. So this implies that the given propositional logic represents a tautology. Hence option B will also be correct. It's not a contradiction, it will always be a tautology. So the correct answer for this question will be B and D. This is a TOC question. We have two languages, L1 and L2. L1 is regular and L2 is context free. Now we have been given these four languages in these options, and we have to determine which of these languages will also be context free. Now the first one is L1 intersection L2 bar, L2 complement. So L1 is a regular language, it has been given. And what is L2? L2 is a CFL, context free language. But what do we have? It is L2 complement. So is CFL closed under complementation? No, it is not closed. But context sensitive language is closed under complementation. So we can say that every CFL is also a CSL. every context-free language is also context sensitive. And because CSL is closed under complementation, this L2, we'll say L2 is a CSL, and since CSL is closed under complementation, so L2 bar will also be a CSL. So this L2 bar becomes CSL. And what we are taking? The intersection of regular language with a context sensitive language. So the result of this intersection will also give us a CSL, context sensitive language. It is not a CFL. So we'll be rejecting this option A. Now what this B is doing? It is L1 complement union of L2 complement and the whole complement. So we can simplify this using the De Morgan's law, and that will give us this upper common complementation would be removed and it will be applied to both of them, L1, L2, and union turns into intersection. So this will again be simplified into L1 intersection L2. So this is how we simplified the option B. And now we know that L1 is a regular language, L2 is a CFL, and intersection between regular and CFL will result into what? It will be a CFL itself. So this option B results into a context-free language. Now this C1, it is saying L1 union of L2 union L2 bar. Now this L2 is a CSL, L2 bar will also be a CSL, but here we will consider the fact that L2 is taken union with its complement itself. So it is like saying a language and its complement itself are combined together. So that will result into a universal set, sigma star. And with this universal set, we can take the union of any other thing, it does not matter. The result will also always be a universal set itself. And this universal language, we know that if, let us say, if our alphabet set is 0, 1, then it will be represented simply as 0 plus 1 star. Or depending upon whatever is our alpha set, we know alphabet set, we know that this sigma star or the universal language, that will be regular. And every regular language is also context free. So we can say that option C also represents a context free language. Now coming to this option D, it is L1 intersection L2. Now we just saw L1 is regular, L2 is context free. So if we take their intersection, it will be also context free. And now on this side, again we are doing the same thing. L1 intersection L2, that will also be a CFL. And finally we are taking the union. So it is CFL union CFL, the result of which will also be a CFL. So this option D also represents a language that is context free. So we got B, C and D, all three as the context free languages. So that is our answer. This is a DBMS question based on functional dependencies. We have a relation U which is having the attributes P, Q, R, S and T, and these are the two functional dependencies that hold on it. And based upon these, we need to determine which of these FDs can be derived from the given functional dependencies. So for this, we can start with getting the closure of all the attributes. So from this relation, P derives QR. This can be decomposed into P derives Q and P derives R separately. Similarly, the next FD which we are having, RS derives T. For this, we cannot decompose it like R derives T and S derives T because they are both collectively deriving T. So now based upon these, we write the closure of all the attributes as P star equal to, it will be able to derive itself, then Q and R. Then for Q, R, S and T, we do the same thing. The closure of Q is Q itself. Closure of R is R. And as we know from here, closure of RS is giving us T. So that is separately because we are taking two attributes on the left hand side. And all of the remaining are deriving themselves. So these are the closures which we have got. And now let us have a look at these options. First one is saying PS derives T. So let us take the intersection of closures of both P as well as S. If we combine both of them, so if there is PS on the left hand side, then we know that P can derive P, Q and R, while R and S together can derive T. So we can say that P will derive R first and then R and S together will derive T. So in effect, this combines to give us PS deriving T. So the first FD can be inferred from the given two. Next one is R derives T. Now here the second FD is RS are collectively deriving T and R does not derive S. So independently R cannot derive T as well. So this FD will not hold true. The third one, P derives R, we have already got that. So it is holding. The last one, PS derives Q. Now since P can independently derive Q, so if we add another attribute on the left hand side which is S, then also PS will be able to derive Q. So this dependency also holds true in this case. So in total we have got A, C and D as the functional dependencies that can be inferred from those given to us. So this is the correct answer. This is a graph theory question. We have been given G, which is a connected, undirected and weighted graph. And for this graph G, we need to determine which of these two statements is or are true. First one is saying that there exists a minimum weight edge in G, which is present in every minimum spanning tree of G. So now, what do we mean by the minimum spanning tree? For a given graph, it is an connected, undirected, weighted graph. So it can be something like this. It can be fully connected graph. There can be ways to reach from each node to every other node. So if we convert a graph into an MST, then what happens is that we make that graph minimally connected, which means there will be a path to go from one node to every other node, but there would be only n-1 edges for n nodes in such a way that the total weight combined of that tree would be minimum. Let us say the edge weights here is like 1, 2, 3, 1, 4, 3, something like this. So if we convert this particular graph into an MST, how would it be like? These are the 4 nodes at their place. We can have 2 different algorithms for achieving this, either Kruskal's or Prim's. And using either of these algos, we will get the MST for this particular graph as this will be edge from A to B, from A to D, and then now we cannot have the edge B to D because that would create a cycle. So we can go for either A to C or B to C. There are 2 choices. We can do this or we can have this edge. So those are the 2 MSTs possible for this particular graph. So what they are saying is there exists a minimum weight edge in G which is present in every MST of G. So in this graph there are 2 minimum weight edges, AB and AD. They have not mentioned that there are unique or there are distinct edge weights. They are just talking about the minimum weight edge. So there can be any number of them. We can have entire graph with minimum edge weights. For this graph, not all of its edges will be included in MST. We will only have any 3 of these 4. It can be like this or like this or like this. So it is not necessary that all of the minimum weight edges will be included in the MST. It may or may not be true depending upon if that edge weight is distinct or not. Here they have not mentioned if it is distinct. So we will say that the statement is incorrect. Now going to the statement 2, if every edge in G has distinct weight. Now here they are explicitly mentioning that G is having distinct edge weights. Then G will have a unique MST. Now if it is having all the distinct weights, let us say in this graph itself, if we change these edge weights into 1, 2, 3 and 4. Now in this graph, if we try to convert it into MST, what would we be doing? We will be going in the ascending order of the edge weights. We will be first including the one with minimum edge weight, then the next, then next. So this is the MST we will be reaching out to. So if there are distinct edge weights, then there will only be single unique MST possible for that graph. There is no ambiguity in that case. So yes, we will say that the statement 2 holds true, but statement 1 doesn't. So we'll be going with option A, saying that S1 is false and S2 is true. So the correct option is A. This is a computer networks question based upon distance vector routing. We have been given the network structure over here. It is using the DVR algorithm for routing. and the partial topology of the network, it is as shown in this particular figure. The objective is to find the shortest cost path from router R to P and Q. So we are having R here at the uppermost level, and at the bottom somewhere we have these two hosts P and Q. Entire topology is not given. In the middle there can be multiple nodes again that we are not actually concerned with. We have to assume that R has three neighboring routers denoted as X, Y, and Z, and during first iteration, R measures its distance to its neighbors. In the first case, it will resolve the distance to its immediate neighbors. Before that, the entire network, let us say, it is having n number of nodes. So for every node X from R, the initial distance would be infinity, and then in every step it will keep resolving the distances. In the step 1, it will resolve its immediate neighbors. Then in step 2, it will resolve those that can be reached in 2 hops from R, and so on. So it measures the distance to its immediate neighbors X, Y, and Z as 3, 2, and 5 respectively. So this happens in the first iteration. Now router R gets the routing vectors from its neighbors. In DVR, what happens? All the neighbors exchange their distance vectors to each other. This routing vector is nothing but the distance vector itself. R will get the distance vectors from all of its immediate neighbors, that is X, Y, and Z. So it gets those DVRs from its neighbors, and that indicates that the distance to router P from the routers X, Y, and Z is 7, 6, 5 respectively. So it so happens that X, Y, and Z are in some way connected to these P and Q, so they already know what is their distance from this P, Q, and R. So they return that thing to their parent, to their immediate neighbor R. Now this cannot be said to be the second iteration. Many iterations would already have taken place, and after all that happens, these X, Y, and Z are able to resolve. They already come to know what is their distance from these nodes P and Q, and so they exchange that distance vector with their neighbor R. So now what happens is, let us draw the topology in this way. We have X, Y, and Z, and then in some way they are connected to P and Q, but we are not actually concerned. We can assume that they are directly connected. So this is how the topology would look like. And what are the distances given? These are 3, 2, and 5. And then for P we have, so for this router P, the distances from X, Y, and Z are 7, 6, and 5 respectively. Similarly, for router Q, the distances from X, Y, and Z are 4, 6, and 8. Decided this way: 4, 6, and 8. So this is what we currently have. And now what are they asking? Which of the following statements is or are correct with respect to the new routing table that will be created at R after updation during this particular iteration? So when these particular distances are returned to R by its neighbors, then it will update its routing table. It will now be able to resolve its distance with both P and Q. So what it will do, it will choose the minimum of all the distances that it is getting. So let us say for node P, it will choose the minimum of the distances RXP, RYP, and RZP. These are the three paths it is having. So it will choose the minimum cost path among these three. What are the costs for all of them? For RXP, the cost is R2X is 3 and then X2P is 7. So in total that is 10. Then the next, which is RYP, for that the total cost of this path is R2Y, which is 2, and for Y2P it is 6. So 2 plus 6 it is 8. Then for RZP, so R2Z is 5 and Z2P is 5. So 5 to 5 is 10. 5 and 5 gives 10, and it will choose the minimum of these r, that is 8. So now the distance r to p has been resolved as 8. Similarly, what will happen for the node q? It will be, again there are three possible paths: rxp, ryp, rxq, ryq, and rzq. So the three distances will be, rxq will be, r2x is 3 and then x2q is 4, so 3 and 4 7. Then ryq it is, ry is 2 and yq is 6, so again 2 plus 6 it is 8. Then rzq, r2z is 5 and z2q is 8, so 8 and 5 13. So minimum of all of them is 8. So the distance r to q will be resolved as 7. So now the routing table of r will be updated. Its distance to p will be updated to 8 and r to q will be updated to 7. So let's have a look at the options. First one is saying the distance from r to p will be stored as 10. No, it will be stored as 8. So that's incorrect. Then the distance from r to q will be stored as 7. That is what we have just calculated. So this is true. And then the next hop router for a packet from r to p is y. So for r to p we got this particular path, that is r, y and p, which means if we want to reach from r to p, then the next hop would be y. So that is the path which has been chosen. So this is also true. And what about the r to q? This particular path has been chosen, so the next hop from r will be on x. And the last one is saying the next hop router for a packet from r to q is, it should have been z over here, but we got the next hop to be x, so again this becomes incorrect. So we'll be going with B and C for this. This is an operating systems question based upon multi-level paging. We have been given a 3-level page table which is used to translate a 39-bit virtual address to a physical address as it is shown over here. So we're having 39-bit virtual address, which implies that the maximum process size that we can have is 2 to the power 39 bytes. But this is the maximum possible size. It does not mean that we will definitely have a process of this much size. We can have even of a lesser size. Let us see what is given. The page size is 4 KB. Let us note down these things. Page size is 4 KB, which means 2 to the power 10 plus 2, which means 12 bytes. Now along with this we have been given that the page table entry size, which means the PTE, that is 8 bytes, and a process P is currently using 2 GB virtual memory, means as we just saw 2 to the power 39 bytes is the maximum possible size, but our process is using just 2 GB, which means 2 to the power 30 plus 1, 31 bytes. So this is the size of the process that we have. So among this total available virtual address space, we are using just 2 to the power 31 bytes. So we will say our logical address space, let us call it, it is 2 to the power 31 bytes, and it is mapped to 2 GB of physical memory. So this logical memory of 2 GB is mapped with the same amount of physical memory, physical address space. So what do we want? The minimum amount of memory required for the page table of process P across all the levels. So in this diagram it can be seen that there is 3-level paging used, and at every level we will have certain number of pages which will be occupying the corresponding page tables. Why do we require this multi-level paging at first place is because we have, let us say, p number of pages in total in our process. Now for these pages we need to create the corresponding page table entries, and when the number of pages grows very large, then what happens is that our page table itself grows so large that it cannot be occupied in a one single page. So that is when we need to divide that page table into across multiple pages. So that is how first we get this level 3 page table. Because it cannot be fit into one single page, we go for this level 2 paging. Again, there the same problem occurs. We still cannot fit them in one page. Then we go for this level 1 paging. Here we have one single page that has the entries. But one thing to be noted over here is that let us call this as PT1, PT2 and PT3. So this is page table in level 1. What will it have as its entries? The entries of the level 1 page tables will have the mapping to the corresponding level 2 page tables. Similarly, the entries of level 2 page tables will have the mapping to the corresponding level 3 page tables. And the entries of these level 3 page table will give us the actual address, the actual frame number where our word will be located. So this is how the address resolution will be done. And the distribution of bits is given as 9, 9, 9 and 12. These 12 bits will correspond to the offset and these 3 9s correspond to the size in those respective levels. So let us see how we'll be dealing with this. First of all, we will find out what is this P, which means the total number of pages in our process. So that will be found as total number of pages equal to the logical address space or our process size divided by the page size. So which is 2 to the power 31 upon page size. What is it? This 2 to the power 12 bytes means 4 KB. So this becomes 2 to the power 31 minus 12, that is 19. So in our process we have number of pages equal to 2 to the power 19. So now what we will be doing this with this, for these many pages we have to create the same number of entries in the page tables. So what we will do is we will have 2 to the power 19 entries in the page. And what is the size of each entry? It is 8 bytes. So this becomes 2 to the power 19 plus 3, 22 bytes. This is beyond the size of a page. Page size is just 4 KB, which means 2 to the power 12 bytes. So this cannot fit into one single page, and hence we will need to go for the multi-level paging. So let us see how that will be done. Now we will start with this outermost, which means this level 3 page table we will be starting with. So there, how many bits are allocated? 9 bits. So that tells us that in level 3 every page has 2 to the power 9 entries. And with these entries, how many pages are to be mapped? All the pages in that process, which means 2 to the power 19 pages have to be mapped. One page is having just these many entries. So what will be the number of pages that the level 3 page table will be divided into? It will be given as the PT3 size, which means the size of the level 3 page table. You can say the number of total entries. There are two ways of getting this. Actually, you can get it as total number of pages like this upon the number of entries per page. So it gives 2 to the power 10, which means in level 3 we will be having, let us write over here, level 1, 2 and 3. In level 3 we will have 2 to the power 10 pages, and each of these page will have 2 to the power 9 entries. So now let us move on to level 2. Now in level 2 again there are 9 bits allocated, which means there are 2 to the power 9 entries again in every page. And what is the total number of pages that have to be mapped? Same as 2 to the power 10, which is the total number of pages in level 3. So here what we will have is the number of pages required over here will be 2 to the power 10 upon 2 to the power 9, which is 2, which means in level 2 we will need just 2 pages. Why? Every page will have 2 to the power 9 entries, and we want to map these many entries, because as we saw earlier, every entry in PT2 means level 2 page table will map to an entry to a page table in level 3, which means this is level 2, this is level 3, there will be multiple pages in level 3, so every entry in level 2 will correspond to one page in level 3. So that is how it works. We got only 2 pages in level 2. So now, is there a need of further paging, or we are done? The thing is, there are again 9 bits allocated to level 1 as well. Let us see why is that needed. At level 2 we have got 2 pages, which means in level 1 we will have 2 entries to be mapped, means 2 pages of level 2 are to be mapped, and again there are 9 bits in level 1, which means there are 2 to the power 9 entries per page. And how many do we have to map? The corresponding pages in level 2. Hence, now in level 1 we will be needing just one single page having these 2 entries. So this is level 1. There are 2 pages in level 2. In this we will have 2 entries, one for this page and one for this page. So now we are done. There will be one single page in level 1. No further paging is required. So now we have got the number of pages in every level. What is the next thing that we'll be doing? We have to find out the total size of all the page tables. So for that, what is the total number of pages that we used explicitly for the page tables? We used 1 in level 1, 2 in level 2, and 2 to the power 10 in level 3, which means 1 plus 2 plus 1024, that is 1027. So these many pages have been used to explicitly store only the page tables. And what will be the size resulting out of this? It is 1027, the total number of pages, and size of every page is 4 KB. We want the answer in KBs only. So the total memory required will be 1024 times 4 KB. This has to be our answer. When we calculate this, it becomes 7 4 28, 8. So 2, 4 twice 8 and 2 10, 4108. So 4108 bytes is the total amount of memory that we need to use explicitly for storing the page tables across all the levels. So answer for this one will be 4108 KBs. An operating systems question based on process scheduling. We have been given 4 options, and out of them we need to identify which of them is or are correct. So it is an MSQ type question. Option A is saying that turnaround time includes waiting time. Now, how do we calculate the turnaround time? We make that table in which we have the arrival time, burst time, completion time, which we derive from the Gantt chart, and then after that we have a column for turnaround time, which we calculate as completion time minus arrival time. So basically this turnaround time includes both the burst time of a process as well as for how long has it waited. For example, a process entered at, let's say, time t equal to 1 unit, but it got scheduled at time t equal to 4 units. So from unit 1 to unit 4, it waited for 3 units of time. So that is its waiting time, and then it completed its execution at t equal to 6 units. So from 4 to 6, 2 units, it had its burst time. So this turnaround time will be the sum of both waiting time as well as burst time, because we will be calculating it as 6 minus 1, which means it's completion time minus arrival time. So 6 minus 1 is 5, and as you can see, waiting time plus burst time 3 plus 2 is also equal to 5. So this turnaround time includes waiting time as well. So the statement is correct. Next one is saying goal is to maximize CPU utilization and minimize the throughput. The goal is actually to maximize both CPU utilization as well as throughput, because throughput is how we are actually utilizing the CPU. This throughput is in similar lines as of utilization. So both are to be maximized, and instead we have to minimize the turnaround time, the waiting time of processes, because if we decrease the waiting time, then turnaround time will also decrease. So this one is incorrect. C is saying that round robin policy can be used even when the CPU time required by each of the processes is not known a priori. A priori means beforehand. If we do not know the burst time of the processes beforehand, can we use the round robin algorithm? Yes, we definitely can use, and it is actually more suitable in these situations itself, because what do we do in round robin policy? There is a fixed time quantum for which we execute each process one by one until it completes. So even if we don't know, and we don't actually need to know even what is its burst time, because we will keep executing it in different slices of time quantum each, and when it expires, then we will call it off. So round robin can be used. The statement is correct. The last one is implementing preemptive scheduling needs hardware support. What is preemptive scheduling? It is a kind of CPU scheduling in which while one process is executing and another high priority process arrives, or if its time quantum expires, then in those situations we need to bring that process out of CPU execution and put another process at its place. So we are basically needing to swap two processes with each other. We need to preempt one and put another in place of that. So this action requires the support of hardware. Hence, implementation of preemptive scheduling requires some hardware support. So statement D is also correct. So we got A, C and D as the answer. Algorithms question. We have been given a directed acyclic graph, or what we call as a DAG. In that, a source vertex is this S and the destination vertex is T. In this, the quality score for a directed path is defined as the product of the weights of the edges on that path. For example, if we have a path from A to B to C and the weights are, let's say, 2 and 3, then for this particular path, its quality score will be defined as the product of weights of edges, which means 2 times 3 equal to 6. Further, for a vertex V other than S, means for all the other vertices except for the source vertex, the quality score of V is defined to be the maximum among the quality scores of all the paths from S to V. It simply implies that, let us say there are two paths, A to B, and let us say C is over here, and even that is taking us to B. Then if the quality score of this particular path, this is not just a single edge, let us assume that this is some path. There may be intermediate vertices in this path, and similarly over here this is some path, not the intermediate, not the direct edge. So for B, the quality score will be defined as the maximum of these two. The quality score, let us say V of B, will be defined as max of the quality score of path A to B and path C to B. So that is how we will be calculating the quality score for all the vertices in this graph. For S, it is assumed to be 1. So what we have to do is the sum of all the quality scores for the vertices in this graph has to be calculated, which means for every vertex of this graph we have to calculate its quality score, and at the end we have to return their sum. So let us take up vertices one by one and calculate their quality scores. So let us start. We will first note down all the vertices over here. We have S, E, D, A, the rest of them here. Then we have F, G, B, E and T. So for each of them, let us calculate their quality scores. For S, since it is the source vertex, they have already mentioned that it will be 1. Then coming to E, it is our vertex E is over. This one was actually C instead of E. This is C. So that's our vertex C over here. What will be the quality score for vertex C? There is only one incoming path to C, that is from S to C, this one. So for this, its quality score will simply be 1. Next, coming to D, it is over here. Now there are two paths that can take us from source to D. The first path is S to C and then C to D. The second path is from S to A and then A to D. We will be taking the max for these two. If we take the first path, that is SCD, then we will get 1 into 1, which is 1. And if we go SAD, then that will give us the quality score of 9 times 1, which is 9. So we will be taking the max of 2, hence 9. Now coming to A, vertex A is here. There is only one incoming edge, so there is single path S to A. Hence its quality score will directly be 9. Now coming to F, F is also having just a single incoming edge, a single path S to C and then C to F. So for this path, its quality score will be 9 times of 1, which is 9. Now coming to G, it is having two incoming edges. Let us clear our graph for better understanding. So now what are the different paths that can lead us to this vertex G? Starting from S, we can go either this way, SCDG, SCDG, or we can go SCFG, SCFG, or we can go SADG, SADG. Is there any other path leading us to G? No, there are just these three. So we'll be taking the max for all of them. If we go by the first path, SCDG, then the quality score will be 1, 1, 9, which is 9. For SCFG, it will be 1, 9, 1, again 9. For SADG, it will be A, D and G. Here it is 9, 1, 9, so 81, and that is the max. So we'll be taking 81. Now coming to B, it is over here. There is only one incoming edge, single path SAB, whose quality score will be the product of 9 and 1, that is 9. Now coming to E, here it is. Now there are again multiple ways for reaching to E. First one would be SA, SC, D, E. S, C, D, E. Next would be S, A, B, E. S, A, B, E. There is no other path possible. There is one more, S, A, D and E. S, A, D and E, this way. So for each of them, let us calculate the quality score. For the first one, which is SADE, it will be 9, 1, 9, that is 81. Then for SCDE, it will be 1, 1 and 9, that is 9. For SABE, it is 9, 1 and 1, 9. So we'll be taking the max, which is 81. So now we are just left with the final destination vertex, that is T. For that also we are having multiple paths, and we'll take the max quality score for it, which means the quality score which will give us the maximum value from different paths. So let us first identify what are the different paths for reaching to T. First one would be SCDGT. Now this is a simple graph with 9 nodes, so we can easily visualize the paths. If it would have been a bit complex, then there would have been some difficulty in identifying all the paths just by visualizing. So for this we can directly go with this SCDGT. Then we have SCFGT, SCFGT. Next is SADGT, Next can be SADET, SADET, and finally SABET. Again, let us calculate the score for all of these. There seems no other path available. And just for verification, you can check out that we have these types of problems while you solve the algorithms question, that if there is a 3x3 grid, then how many paths are there to reach from the top left corner to the bottom right corner, and we have mathematical formulas for evaluating that. For example, in this case there are 3 nodes, so we have the permutation and combinations from which we can find out the exact number of ways, and you can just use that to check if we have completed all the possible paths or not. So that is a way in which you can verify. Over here, let us calculate for all of these paths. For this SCDGT, what do we get? SC, D, G and T we get simply 9. For SCFGT, we will be getting SCFGT again 9. For SADGT, SADG and T, it is 81. For SADET, it is SADENT. So in this path we are having 3 9s, SADET, 3 9s, hence we get 729 for this. And finally SABET, 2 9s, so 81. So obviously we will be getting 729 for this. So now we have calculated for all the vertices and we simply have to return their sum. So let us find out what their sum is. From here we get 18 plus 2, 20. And from these vertices we get 729 and 90 and 90, which is 180. 180 and 20 is 200. So we get 729 plus 200, that is 929. So that would be the answer for this question. The networks question based upon pure Aloha access control mechanism. Here we are using pure Aloha for transmission where each frame is of length 1000 bits. So the length of frame is given as 1000 bits. The channel transmission rate, or you can say the bandwidth, it is given as 1 Mbps. And here it is 1 megabits per second, not the bytes. The aggregate number of transmissions across all the nodes, including the new frame transmissions and the retransmitted frames due to collisions. So here we don't have to consider the retransmitted frames once again, they are already included in this. So this thing is modeled as a Gaussian process with a rate of 1000 frames per second, which means in 1 second there are in total 1000 frames being generated, and that includes both the new frames as well as the retransmitted frames. So if in 1 second we are having this much, we have to actually determine the throughput. The definition has been given. It is defined as average number of frames successfully transmitted per second. So this 1000 is the number of frames we are trying to transmit, or we are generating actually in 1 second. But throughput will be the average number of frames that are successfully transmitted per second. So that is what we need to find out. So coming here, in 1 second we are generating 1000 frames. So in one transmission time, in 1 unit of transmission delay, what is the number of frames that will be transmitting? Let us find out that. For that we will first need to find out the transmission time, or you can say the time it takes to transmit 1 frame. That will be given as the length of frame upon bandwidth. So it will be 1000, which is the length upon bandwidth, that is 10 to the power 6 megabits per second. So this gives 1 by 10 cube seconds, or you can say 1 milliseconds. So the transmission delay is 1 millisecond. Hence in 1 second, if we are able to generate 1000 frames, then in 1 milliseconds we will be able to generate exactly 1 frame, dividing both these sides by 1000, which means in one transmission delay we can transmit 1 frame. And in case of pure aloha, what do we define this G as? This factor G, it is the average number of frames in one particular frame transmission delay, the average number of frames that we attempt to transmit. So if this is modeled as a Poisson process, then we will be able to say that the throughput for this is, it will be given as G times of e raised to minus 2g. And for this case, the value of G is simply 1, just because in this case the transmission time is 1, so the value of G also becomes 1 for this pure aloha. And hence if we calculate the value of this, it will become G, which is 1, then that times of e raised to minus 2, then this G is again 1, so this is simply 1 by e square. What is this e? It is the Euler's number. You can say the Euler's quotient, or that thing whose value becomes 2.7 something. So when we do this e squared, and after calculating this thing, it turns out to be 0.1354 something. And we are asked, this was for 1 millisecond or for the one transmission time itself, but we want throughput which is defined in per second. So this was in 1 millisecond. So when that is mapped to 1 second, then it would become 0.1354 times of 10 cube, which gives 135.4, and we'll be rounding it off to 135. So that will be the actual throughput, which means in 1 second 1000 frames were being generated, but only 135 out of them are being successfully transmitted. So throughput for this pure aloha system would become simply 135. So that would be the answer. The data structures question based upon the tree data structure. They are talking about a complete binary tree with 7 nodes. So what will be the structure of this tree? It is complete, so every node will be having 2 children like this, and there are just 7 nodes. So this will be the tree. In this tree, let A denote the set of first 3 elements obtained by performing a breadth first search starting from the root. So let us call this root R. From this root, if we perform a BFS, then we will get a set A of the first 3 elements. So at this node R, when we perform the breadth first search, what is the nodes we will get? Let us call these 1, 2, 3, 4, 5 and 6. So starting at this root R and performing a BFS, what is the set of first 3 nodes that we will get? So definitely R will be one of them. Then after that we will be visiting this one. And since it is a BFS, so we will go level by level. So this level has to be completed first. Hence after 1 we will be visiting this 2. So this forms our set A of the first 3 elements obtained by performing a BFS. And in the similar way, they are saying that the set B denotes the set of first 3 elements obtained by performing the DFS from the root node itself. So if we perform a DFS, then that represents set B. And what are the 3 elements that we'll have? First, the root, of course. And then in DFS, what we do? Let us say if we visit 1 first, then after this 1, what is the next node that we'll visit? The children of 1 and not the children of root. So we can visit either 3 or 4 next. So there are different sets we can get for this. It can be R1, 4 as well, or it can be R. And instead of 1, we can also visit this 2 first. So it can be R2, and then next can be one of these 5 and 6, which are the children of R. So we can have R2, 5, or we can have R2, 6. So these are the different possible sets B that we can have. So now what is the next thing they are saying? The value of this modulo symbol A minus B. What does this represent? This is not modulo, actually it is talking about the cardinality of the sets. We already know the cardinality of both sets A and B is 3. Both are having 3 elements. So if we take the difference of those two sets, then for that resulting set, what will be the cardinality? That is what they are asking. So if we take the difference of these sets A minus B, then what the result will have? In all of these we are having the root R. all 4 if we consider, then all are having R, so this will definitely be gone. And then if we consider these 2, then they are also having this 1 with them. So for these 2 cases, the difference set that we will get is R and 1 are both present, but this 2 is not present in any of them. So in that case, we'll get that result as 2. And if we take the last 2 sets B, then for that A minus B will give us this R is present in both, so that will be gone when we take the difference. Then this 2 is also present in both, so that will also be gone. While taking the difference of 2 sets, what do we take? The element which is present in A but not in B. That is what we mean by A minus B. If A and B both are the sets and we are performing this subtraction operation on them, then we will take those elements of A that are not present in B. So here R and 2 both are present, but this 1 is not present. So in this case, it will result into this 1. So whichever we consider, the cardinality of this set is always going to be 1. Whatever representation of set B do we consider, whichever A minus B do we take, the cardinality of resulting set is always going to be 1, and that's what they are asking us. Hence the value of this cardinality of set A minus B will be 1. So that is our answer. This is a TOC question from Finite Automata. They're saying that suppose we want to design a synchronous circuit that processes a string of zeros and ones. So the input alphabet will be 0 and 1 both. And then given a string, that automata has to produce another string by replacing the first one in any subsequence of consecutive ones by a 0. Which means if you encounter any subsequence consisting of all the ones, such as 1, 1, 1, triple 1 and so on, then that has to be converted into, only the first one will be converted to 0 and rest of it will stay the same. 1 0 0, or no, this would become 0 1. Similarly, the first one will become 0 and then rest of them will be remain same. So this is what the modification has to be made. So they have given an example. This is the input sequence, and as we can see in this particular character, that 1 has been changed to 0. Then here we had a consecutive ones in which the first one has been changed to 0 while the next one has been retained. Similarly, here we had another subarray of 0 in which first has been converted to 0 and rest of them are kept as it is. So what modification we have to do using this finite automata? We have to find out a subsequence of consecutive ones, and then we have to replace the first one in that with a 0, and rest of them will remain the same. So for performing such an operation, a Mealy machine has to be designed. It is a state machine where both the next state and the output are the functions of the present state and the current input. So that is the definition of Mealy machine which they have given. The above mentioned circuit can be designed as a two-state Mealy machine. So for performing this particular operation, we have to design a two-state Mealy machine in which the states can be represented using Boolean values 0 and 1. So they're saying that the given problem can be modeled as a two-state Mealy machine in which the states will be 0 and 1. We denote the current state, next incoming bit, and the output bit using these variables S, T, B, and Y respectively. Then for them, the values have been asked. So first of all, let us design the machine itself, and then we'll see what are those variables to deal with. So as we can see, this initial state is 0, and from this state, if we get the input variable as 0, then what we'll do, we will stay in the same state, and because this is a Mealy machine, an output will be associated with this input, which will be written along with it in this particular way. But for this state, if input is 1, then as we saw, that first one has to be converted to a 0. So we will go into this state if the input is 1 and we'll convert that to a 0. So this will be the transition. Then coming to this state 1, from here, this was the first one and we have already converted this one to a 0. So now whatever ones are left, if any, then they would be left as it is, which means there will be a loop in this state, and whatever ones are there, they will be kept the same. And afterwards, if from this same state, if we get the output as 0, then we will go back to the initial state, and that 0 will be kept as 0 itself. So this is the Mealy machine that will be designed for this problem. Now let us come to these 4 variables. So now a Mealy machine, we have 4 parameters: the current state, and that current state is being denoted here by S. Then we have the input symbol. That input symbol is being denoted with this next incoming bit. It is B. After that we have the output. For output they have used the variable as Y, and at the end we have the next state for which they have used this T. So let us fill out this table from the given machine. As we can see, the current state is 0, and for that we can have the corresponding input bits as 0 and 1. So these will be the entries in it. Similarly, when the current state is 1, we can have input as 0 and we can have input as 1. So these are the 4 rows we will have in this table. Let us fill out it. When our current state is 0 and the input symbol is 0, which means this current state is 0 and the input is also 0, then what are we doing? We are looping into the same state, which means the next state is also 0. And what is the output? Here we can see output is also 0. So that is what we get. Then next is current state is S, input is 1. Sorry, the current state is 0, which means this one, and the input symbol is 1, which means this particular transition will be used. And what does it result into? It results into the next state being a 1. And what is the output? It is 0. Similarly, when we are in the state 1 and the input symbol is 0, which means the slower transition, then the next state is 0. And what about the output? Output is also 0. Finally, when we are in the state 1 and the input is also 1, then we go into this particular loop. The next state is also 1 and the output is also 1. So that is how our table gets filled. Now what we have to do? We have to find out the corresponding values of T and Y in terms of S and B. So let us see how that can be done. From this table we can see that when these two are 0, T is 0. When it is 0, 1, then T is 1, which means this is definitely not an AND operation. Then when it is 1, 0, T is 0. For 1, 1, T is 1. So as we can see, in B we have 0, 1, 0, 1. In T also we have 0, 1, 0, 1. So we can simply say T equal to B. That is the expression we got for T. And now coming to the next one, which is Y. As we can see, when both are 0, Y is also 0. When it is 0, 1, then also Y is 0. For 1, 0 also it is 0. And only for the last 1, 1, it is 1. So we can say Y equal to S and B. The other way for doing so would have been to create a K-map and then check out what are we getting in this way. But because there were just 2 variables, so it was not necessary to do so. ST, then we would check out for both T and Y respectively by filling out this 2 cross 2 K-map. But it was simple to visualize itself in this way, so that is what we did. For T we got B and for Y we got SB. So that matches with this option B. So that will be the correct expressions. So we'll be going with it. As a digital logic question based upon number system, we have been given 2 numbers. This one is represented in base 2 and the right one is in base 10. Both of them are equivalent. We need to determine the values of x and y and then return their sum. So now there are 2 numbers in different number systems. So in order to compare them, we will need to convert them into the same system. So what we can do is the left side one, which is in base 2, we can convert it into base 10 and then compare both. So now this is a floating point representation, 0.1101, and the digits are towards the right side of the decimal point. So if we have to convert this number into decimal, then we will be using the negative powers of 2, which means for the first one, the weight factor will be 2 to the power minus 1, or we can say 1 by 2. For this it will be 1 by 2 square. For 0, 1 by 2 cube. And for this one it will be 1 by 2 to the power 4. In the same way as we do 2 raised to, if let us say here we had the numbers, then how do we take the weights? 2 raised to 0, 2 raised to 1, 2 square, 2 cube, and so on. That is for the left side of decimal point, but we are moving at the right side. So here weights are in the negative, and that starts from 1. So it is like 2 to the power minus 1, minus 2, minus 3, and so on. And hence now, since we have the weights, we can calculate its decimal value as the given bit into its weight factor. So 1 into 1 by 2 plus 1 into 1 by 2 square plus 0 times 1 by 2 cube plus 1 times 1 by 2 to the power 4. And this becomes 1 by 2 means 0.5 plus 1 by 4, which means 0.25 plus this one is 0. The last one is 1 by 16, which is 0.0625. When we add all of them together, we will be getting 0.8125. You can check it out. 0625, 0.5000, and 0.2500. It will give us 25118125. Now we will compare it with the given number, which is in base 10 itself. The first bit 8 is matching, 5 is matching. Hence this will be our x and this is our y. So x equal to 1, y equal to 2. We can straightforward do the comparison between them. There is no need of any further conversion. So we got the values of x as 1 and y as 2. And we need the decimal value of x plus y. So it will simply be 1 plus 2 equal to 3. So that is our answer. Programming question. We have been given a C program, and for that there are these 4 statements among which we need to identify which of them is true. So now looking at this program, first they have defined a structure with the name node. So basically a node structure has been given to us in which every node has a int value and it has a next pointer. Then using that node they have initialized this box E, head, box N. Those are the 3 nodes they have defined out of it. And then there is an integer variable index initialized with 0. So now what they are doing is box E and head, they are both referring initially to the same node. This is box E and the head. And using this dynamic allocation, they have newly allocated a node, and these 2 pointers are referring to that node initially. Then this head value, which means the value of this node which has just been created, it is initialized with the index. And what is the value of index? It is 0. So such a node is created, and now they are moving into this for loop in which that same index variable is used with initial value 1 and going up to 3, incremented with 1 at each time. So this particular loop will run for 3 times. And what is it doing? This box N, which was a variable referring to this same for type node, that has been used and a new node has been allocated, which means what will happen is a new node will be created. Box N will be the pointer referring to it. And for this new node, what are they doing? Box E next, which means the next pointer of this existing node is now pointing to this newly created node, and the value it is being assigned is the index. So for the first iteration it will be 1, which means such a new node is being created and the next pointer of box E is being assigned to that new node. And after that, box E equal to N, which means this box C is incremented, and now it is also pointing to this new node. And this thing happens for 3 times. So what they are actually trying to do is they are fixing this head variable at node 0, and they are using this box E variable in order to traverse in this particular linked list which is being created. In next iteration, they will create a new node in which the value will be 2 because the index value is being used. That will be referred by box N, and after making this pointer, even this box C will move to the next node. So that is what will happen. In the last iteration, this 3 will be created. Box N will be the name referring to it. This next pointer of 2 will be assigned to 3, and after that even this box 3 will move to the last node 3. And after this the index variable will become 4 after this increment. So this condition will fail and we will come out of the loop. So after completion of the loop, what do we have? We have a linked list like this: 0, 1, 2 and 3. And what are the pointers? At 0 we have the head, then at the last node 3 we have both box N as well as the box E. So now what happens? There is another for loop in which this index is being run from 0 till 3, incrementing with 1 at each time. And in this loop, what are we doing? We are printing value at index %d is %d. And what are they using there? Index and the head value, which means while index is 0, what will they be printing? Let us write that here. So in every iteration, 2 print statements have been given. Let us see what does that print. It will print value at index. And what is the value of index in first iteration? 0. So value at index 0 is head value. What is the head value? It is 0. So this will be printed. Then head moves to the next node. So now this head will move from 0 to 1. And because now there is no reference to 0, so this node will be lost, or we will say that first node or the head node has been deleted and we are moving to the next node. Because previously while creating the list we were using this box E as the iterating variable, but now head itself is being used. So as head moves ahead, the previous nodes will keep on getting deleted. So now head moves to node 1, and we are again printing value at index is what it is, but value of index is still 0. Hence value at index is still 0, hence they are adding 1 to it. So 0 plus 1, 1 is head value. Now head is at 1, so it will print it like this. So that was the first iteration of the loop. Then in the next iteration, value of index will become 1. So what will it print? Value at index 1 is 1. This will be printed. Then head will move from 1 to 2. 1 will be deleted. Then it will print value at index 2 is 2. That was the second iteration. Now this index becomes 2, and this time what will it print? The value at index 2 is 2, and head will move ahead from this. So now head comes to 3, and it will print this statement value at index 2 plus 1, which is 3. And what is that value? Head value. So 3. And then comes the last iteration when index becomes 3. Here what will happen is it will print value at index 3 is 3. So this is printed, and now head moves ahead. But now after 3 there is no initialized node, and we haven't even initialized it to null. That would have been true if over here when we did this box E equal to n, we should have added a line box at next equal to null. Then in that case the next node of 3 would be null. But because that has not been done, then it is possible that after 3 whichever location is there, there might be some value stored at that location. So it is possible that we may end up getting a garbage value or we may end up getting null, but for sure in either of the two cases we are not going to reach at any initialized node for sure. So now when we try to increment this head to the next node of 3, it will definitely raise an error, and we are trying to access that particular index and print the value stored at it. So now this actually becomes dereferencing an uninitialized pointer because we did not initialize it ourselves. It is possible that that particular memory location is valid and some value might be stored in that particular location, and since we did not do it and we didn't even initialize it as null, so this is going to cause an error. So going with this option D, it dereferences an uninitialized pointer which may result in a runtime error. Why have they used this may? Because it is possible that the location next to 3 may or may not be null, it may or may not have some value, and we are trying to access that particular location. So hence this may raise a runtime error. And what error will be reached? That you are trying to access a location which does not exist, in case it is an invalid location, because that depends upon which address it is. So this would be the most appropriate choice to go over here. What about the other options? The program creates a linked list of 5 nodes. That is definitely wrong because the list created initially had only 4 nodes. Then the next one, upon execution, it goes into an infinite loop. No, this is false. Both of these loops were finite, but just in this last print statement, we encountered an error because this head value was not accessible there. Then the next option, it has a missing return which will be reported as an error. So again, this is not true. At the end of this, we might add a return 0 thing because it is int main. That is not actual cause of error in this. The particular line which is causing error, it is because of dereferencing an uninitialized pointer. So we'll be going with option D. This is a compiler design question. We have been given this C code and we have to answer that which of these phases in a compiler will throw an error for this code. So now looking at this first line, int main, there is no error in this. It is as per the standards which actually exists there. But coming to the second line, integer x. Now here what happens is integer and x. The first phase of the compiler, which is the lexical analysis phase, as we all know, what will it do? It will check for these integer x followed by the semicolon, and it will find that all of them are valid identifiers. So it will treat this integer x semicolon, all of them as different identifiers. Because if we had to declare a type in C, then what is the syntax that we use? For the type, we would have used small int in order to denote the integer type. But if we write this entire integer, then that is not a valid reference in C language. So this gets treated as an identifier. So now what does this lexical analysis phase do? It says that integer and x, they are both different identifiers. So it successfully parses that and converts it into a stream of token. So there is no error in this lexical phase. Next we go to the syntax analysis phase. In that what happens? It gets as input a stream of tokens in which this integer and this x both are stated as identifiers, and as per the rules in C language, it is not allowed to have two different identifiers next to each other like this because there is no operator between them. They are simply two identifiers next to each other. So this theoretically has to throw a syntax error as well. So for the timing, let us say syntax analysis phase will generate an error that is a valid candidate for our answer. But if we actually try to compile this code and check it out, then what happens is that it simply says that this integer, this particular keyword, it is an undeclared identifier. So it is actually confused whether to call this as a keyword, as an identifier, as a literal? What exactly should it be? Because this is not a valid way of declaring a type, and this is not a variable instead. So when we try to compile it, the error thrown is that this integer word is an undeclared identifier. And in which phase does this error gets thrown? Such an error is thrown in the semantic analysis phase. So going practically, we see that the error appears in semantic phase and not the syntax analysis phase. So this can also be a valid answer. Then machine dependent optimization, there is nothing as such required for this code, and in the previous phases only we are getting the error, so we are not actually going to check for the next levels at all. So this is definitely not a valid candidate. So now from these two, this was an MCQ question, so only one had to be correct. So that was a little debatable which phase to go with. And as per official answer keys, and even if we check it out practically, then we get that it is the semantic phase which will raise error instead of the syntax analysis phase. So that is what we'll be going with, the option C as our answer. This is an algorithms question, actually based on Huffman coding. They have given us a string, this one, and each letter in the string has to be assigned a binary code satisfying the following properties. So using these two properties, we have to assign some encoding to the string and then determine among the set of all binary code assignments that will be given to that string, satisfying these two properties, we have to determine what will be the length of this encoded string, which means for each character of the string we'll be assigning some binary code, and then what will be the length of that encoded string. That is what we need to answer. So let us have a look at what the two properties have been mentioned. For any two letters, the code assigned to the one letter must not be a prefix of the code assigned to the other letter. This is the property of Huffman code, and from this property itself we understand that they are talking about Huffman coding, because Huffman code is also called as the prefix code, and the code assigned to one letter does not become the prefix of code assigned to other letter. So from this we understand that Huffman coding has to be used. And the next property is saying that for any two letters of the same frequency, the letter which occurs earlier in the dictionary, which means if, let us say, in our example B, C and D all are having same frequency. So when such collision happens, then the letter which occurs earlier in the dictionary, which means B in this case, the one which is alphabetically smaller. So what has to be done with it? It is assigned a code whose length is at most the length of the code assigned to the other letter, which means for the alphabetically smallest letter, what we have to do is the length of the code which will be assigned to that letter, that has to be at most, which means less than or equal to this one. It has to be less than or equal to length of code assigned to the others, which means the one which comes alphabetically first, that has to get a smaller length code. And when does this happen? When it lies on the upper levels of the tree, because leaf nodes will get the maximum length code, and those nodes which lie on the upper levels, let us consider this tree for example. Here let us say we have P, Q, R, S, T and U. So in this case, let us say this U and T, we are considering them. So what is the length of the encoding which this U will get? It will be 1, 2 and 3. It will get a 3 length code because it is at a distance of 3 from the root. But this node T lies on the upper level from U. Both are leaf nodes, but T is at the above level, so it will get only 2 length encoding. So from this BCD we'll have to place B over here and D at the bottom. So now following all these properties, let us find out the encoding for this given string. Let us note down the frequencies of all the letters. For A it is 1, B, C and D it is 2, and for E the frequency is 3. So now we have to construct the Huffman tree for this string. So we will be starting with the one having least frequency, that is A. So let us construct A over here with frequency 1. Now this B, C and A all are having same. So what we will be taking first? At the bottom level D will come and on the top levels B will come. So we will pick up D first and make it a neighbor of A. So this will be something like this. So now A is done, D is done. So we have B and C now. Both of them will be taken at the same time. So we can have it like this. B and C both with frequency 2 taken over here. So now we are done with them. This E is left with a frequency of 3. So we can take it on the either sides of 3. Let us take it here. E with 3. Then these 3 and 3 will make up 6. And finally this 6 and 4 will be combined to become length 10. So this is how encoding will work out. And now we have to find out for all A, B, C, D and E what is the length of the encoded strings they have got. So we can go with 0 on the left and 1 on the right, or we can also go vice versa. We are not actually concerned with what encodings they are getting. We are concerned with the length of the encoding they have. So let us go with 0, 1 notation. We can also go the other way around. So with this, A is over here. What is its encoding? It is 0, 1, 0. For D, it is 0, 1, 1. Then coming to B, it is simply 1, 1. For C, it is 1, 0. And for E, it is 0, 0. So we have got an encoding for all of them. Now, in order to find out the length of the total encoded string, what we'll do is we will multiply the length of these encodings with their frequency. So for A, the length of its encoding is 3, then 2, 2, 3, 2. These are the lengths of their encodings. And now we will write down their frequency next to it. Frequency of A was 1, B, C and D was 2, and for E it was 3. So we'll just multiply them all and take the sum. So that will give us 3, 4, 4, 6 and 6. And what is the sums up to? 3 and 4, 7 plus 4, 11. 11 and 12 is 23. Which means the total length of this encoded string for the given string will be 23. So that is our answer. This is an engineering mathematics question. There are two sets, S1 and S2, defined as the following, and need to determine which of these statements about these two sets is or are true. The value of n is given to be greater than or equal to 2. Now, based upon these facts, let us evaluate what the resulting sets are. Set 1 is a set of all n cross n matrices having the entries from set having elements A, B and C. So how many such matrices will exist? That will, all those matrices will be forming this particular set. The set is having all n cross n matrices, and value of n can vary. It is given to be greater than or equal to 2, so we can set the value of n to be 3, 4, 5 and so on. And for every value of n, let us say for 3, we will be having 3 cross 3 matrix, and each element of this matrix will be coming from this set. So this 3 cross 3 matrix, it has 9 elements and each of these elements is coming from this set. So how many 3 cross 3 such matrices will be there? There are 9 elements and each has 3 choices. So it will be 3 to the power 9. Similarly, if it were a 4 cross 4 matrix, then there will be 16 elements. Each has 3 choices. So 3 to the power 16 and so on. If we generalize it for value of n, we get 3 to the power n squared as the cardinality of this set S1. It will have 3 to the power n square such matrices, which implies that for a given value of n, there are 3 to the power n square such matrices which satisfy the given conditions. Okay, now we're done with set S1. We have found out its cardinality. Now let us move on to set S2. It is a set of all functions from this set, let us call it A, to this set B. Now this set A, it is having elements from 0 to n square minus 1, which means n square elements. That is its cardinality. And set B is having just 3 elements. We have to find out the number of functions from set A to set B. Now what is a function? Function is such a relation from set A to set B such that every element of set A will be mapped to some element of set B. It is possible that multiple elements of A map to the same element of B, but it is not allowed that one element of A maps to multiple elements of B. This kind of thing is not allowed. This is allowed. And another condition is that no element of A should be left out. It is not allowed that if it is having 3 elements, this is having just 2. So this is how we map and this is left out. That's not allowed. Either you can map it to first one or second one anyways. So it is allowed if elements are left out in B, but none of them should be left out in A. That is the condition. So now our set A is having n square elements and set B is having 3 elements. So how many functions can be formed? That is the question. So what we can do is we can pick up every element of A one by one and map it to one of the elements of B. So each element of set A has 3 choices, either 0 or 1 or 2, and there are n square such elements. First is having 3 choices, second is having 3, third is having 3, so on n square times. Each element is having 3 choices. So we are having 3 multiplied by itself how many times? N square times. So what does this become? It becomes the same thing, 3 to the power n squared. So our set S1 and set S2 both are having the same cardinality, which is 3 to the power n squared. Now let us look at the options and determine what is correct. There does not exist a bijection from S1 to S2. What is a bijection? It is such a mapping which says that there are different types of functions. Let us note them first: injective, surjective, and bijective. Injective means one-to-one mapping. Every element of set S1 has to be mapped to, like one element of set S1 maps to one element of set S2. There is a one-to-one relation. And surjective means onto, which says that no element of B should be left out. All of them should be used. So in this case, from S1 to S2, if there has to be a surjective mapping, then all elements of S1 will be used, all elements of S2 will also be used. That is called surjective. And bijective is a combination of injective plus surjective. It is 1, 1 on 2. So the first option is saying that it does not exist a bijection from S1 to S2. There can exist a bijection because see, S1 is having the same number of elements as S2. So it is possible that we create such a mapping that it is one-to-one as well as onto. There are multiple mappings possible, but there also exists one particular matching in which the relation will turn out to be both 1-1 as well as onto. We will use all elements of S1, we will use all elements of S2, and we will ensure one-to-one mapping. That is definitely possible. So there exists a bijection from S1 to S2. So this option A is incorrect. Now B is saying there exists a surjection, which means onto. Definitely both are having same number of elements, so we can create a surjection between them. There exists a bijection, definitely. Surjection and injection both can exist, so they will combinedly make up bijection. There does not exist an injection. No, it is false. Injection does exist. One-to-one relation can be formed. Now, it is not necessary that we always have to form one-to-one relation and onto relation between them. They are just asking if it can exist or not exist. So we are answering that yes, it can exist in particular cases, in a particular way if we create that mapping. So it is definitely possible to have a bijective relation between S1 and S2. So the correct answers are B and C. This is a DSA question on heap data structure. We have H, which is a binary min heap consisting of n elements implemented as an array. We need to determine what is the worst case time complexity for performing an optimal algorithm that finds the maximum element in this heap. So now H is a min heap, and in this min heap we need to find out the maximum element. If it were the minimum element, then it would be the first index. We could have directly got it in order of 1 time. But this is a min heap, and in that heap we need to determine maximum element. So we know that what is the property of min heap? That the parent will be lesser than both its left child as well as the right child. If this is 2, then its children can be 4 and 3, something like that. So if in this min heap we have to find the maximum element, then where would it be present? In one of the leaf nodes. These are the leaf nodes, and in any one of the leaf nodes that maximum element can be present. It is not necessary that the leaves are in sorted order. It can be any way, like let us consider this particular min heap. This is 1, 3, 2. Then any element greater than 3 we can have here 4, 5. Then something greater than 2 we can have, let's say 8, 7. Anything is possible. So these leaf nodes do not need to be in the increasing order. They can be anyhow present, but we are knowing that the max element will be one of these. And so we know that in a min heap, what is the number of leaf nodes we can have? It will be order of n by 2, or we can say order of n, because when we store it in the form of array, then the index of this first leaf node, it turns out to be n by 2. Then we take the floor and so on. We'll keep on going from n by 2 onwards. This will be n by 2 plus 1, then next will be n by 2 plus 2, and so on. So in this array, we will actually need to check out the second half of it, which means the elements from index n by 2 till n. So we actually need to perform a linear search on half of the array. We cannot perform binary search because these elements are not in the sorted order. So what we will do is, this is our array. This is an n by 2th index. This is the nth index. So from this part to this part, we'll be performing a linear search, and that is how we will be finding out the maximum element. So the time complexity for this algorithm would be order of n, because we are performing a linear search. Hence the correct answer is C. This is an engineering mathematics question based upon probability. They are saying that we have a biased coin in which the probability of getting the outcome on a single toss as head is 0.4. So for a single toss, probability of head is 0.4. Hence the probability of getting a tail on a single toss will be 0.6. Now this coin is tossed 1000 times. So let us call n to be the number of tosses, which is 1000. Now let x be a random variable that denotes the value about number of times the head appears in these 1000 tosses. So we are tossing this coin 1000 times, and this x gives us the expected number of heads in these 1000 trials. So we want to calculate not the expected value itself, we want to find out the standard deviation of x, because this x is a random variable. So we cannot simply find out, we can't simply say that there are 1000 tosses and for every toss the probability of getting a head is 0.4. So we can expect 400 heads in the entire number of trials. But that is not what they have asked us. We want the standard deviation of x. So what approach we will be going with is, since this 1000 trials are independent of each other and for each trial these two outcomes are existing, so this thing can actually be mapped as a binomial distribution. That is what we'll be going with. So using binomial distribution, what do we do in that case? There we have this n as the total number of trials, which is 1000. Then we have the number of success denoted as p, which in this case will be probability of getting a head, and that is 0.4. Then we denote q as the failure probability, which will be 0.6. So using these three parameters, we say that the variance for this random variable x, or you can say v of x, will be n, p, q. product of all three. So that will be 1000 times 0.4 times 0.6, which becomes 240. So this is how in case of binomial distribution we calculate the variance for a random variable, and now using this variance we can reach to the standard deviation or sigma of x that is given as the square root of variance. So in that case it would become root of 240, which would be 15 squared is 225, so that has to be 15 point something. When we calculate this, it turns out to be 15.49 approximately. So we had to report this answer to two decimal places, so we will be simply going with this 15.49 because this is the actual standard deviation of x. So that's our answer.